Uh, Once again, I'm John Mallinckrodt, your host for Physics. Welcome to number 81. And we're going to be talking about mass and weight today. I woke up this morning actually thinking that I was just going to have an open topic, not really do anything this week. And then it occurred to me my perennial favorite thing to talk about is gravitational force, not within relativity so much, but just the conceptual idea about the gravitational force that I think is just really useful. And I'm hoping through talking about mass and weight to convince some of the skeptics here. And I think Hero Andy is a bit of a skeptic when I talk about things, when I say stupid things like gravity is not a force, which it isn't in general relativity. And I get that skepticism. But we're going to see today, I think, why even if you want to continue to work within the Newtonian paradigm, it's really useful to understand what we mean when we say in general relativity that gravity is not a force and that it's frame dependent, that the gravitational field is frame dependent and all of that. Because one of the things that we'll see is there's just a lot of confusion about weight in particular and its relationship to mass that starts with just the fact that we live on the earth where the two things are easy to confuse, but is compounded by the Newtonian paradigm, which isn't to say that the Newtonian paradigm isn't a good one to use, but it is to say that when you start talking about weight and gravitational force in the Newtonian paradigm, confusion is inevitable. You simply can't erase the confusion from the Newtonian paradigm. So it's nice to kind of layer the general relativistic paradigm over that. And so that kind of summarizes, I guess, the blinding flash I had this morning in deciding to talk about mass and weight today. So that's what we're going to do. And it's I have a large number of slides, but most of them are pretty quick, I think. So I don't expect this to be as long as the usual presentation. Let me say hello to a few people. Shamash, who helps me stream these, doesn't help me stream. He completely takes over streaming these to YouTube and then compiling them on the Scientific Discourse channel on YouTube. Shamash, thanks for doing that. Did you want to say hi, talk about your Philosophy Wednesdays maybe for a moment?
Sure. Hello, and sorry for interrupting you a minute ago.
No problem.
It's my
I should coordinate with you before I start these things.
no problem. It's my pleasure to arrange it. It has become easier and easier the more we do it. So it's a procedural thing, and it is our pleasure to have you as our physics teacher because you are great and we love you. And I'm also happy that you're using the words we are doing, we are discovering in the Philosophy Wednesday series. You kind of slipped in a paradigm here during your speech. So I'm really happy that it's a good thing that these things are meaningful. And we will be talking about the reason I mentioned is that we talked about Thomas Kuhn in the previous episode last Wednesday, and Thomas Kuhn is the one who popularized this terminology, and we will be talking about him next week as well.
Yeah, I should mention that I did, as I mentioned in Philosophy Wednesdays last week, that I had a course called The Psychology of Science when I was an undergraduate that was really a good course and that focused on the structure of scientific revolutions by Thomas Kuhn. So I was introduced to the paradigm and came to my vocabulary from Thomas Kuhn and that book as well. And it is a good word. Andy, hero protagonist, thank you for coming. Welcome. I want to say hi.
Good morning. Good morning. That was a nice live version of Gravity. I always like hearing the extended play version of a song. It was good. Does he play slide or does he play just slidey?
It's interesting you say that because it's very clear from that version that he does play slide, and I had not appreciated that before. He gets this beautiful nuance in his guitar solos, and I had always thought he was just a master string bender, but it's pretty clear that he's actually up there in the Daryl Trucks league as a slide guitar player. Yeah, I found that version of Gravity, which is one of my favorite play-out songs, just this morning as I was looking for another song having to do with gravity, and I came across that one, and it is gorgeous, and it goes on for a while. I didn't play the whole thing, and I haven't even heard the whole thing, so I'm going to be listening to that one more too. Hermes, welcome. Did you want to say a few words?
Good morning. Yeah, this is amazing. Yeah, I love these rooms, and I agree with Shamash. I learned quite a bit from you. I did have a lot of questions in regard to mass and weight, but I will wait when
Oh,
you.
you'll have no questions when we're finished. So,
All righty, all right.
and if you do, just ask. And Ben, last but not least, Ben Tristram.
Hey
Thank you
man,
for
how you
being here,
doing?
Ben.
Yeah, you're making me miss doing my rooms, to be honest. Yeah, nice to be here. I'm on an exercise fight, so if I do come off mute, I might be panting, um, but it's all good. I'm supposed to be at conversational pace, so we'll find out if that's working. Yeah, I enjoy mass and weight as a topic. Is cool. I regularly have to check myself when using the relevant terms, and yeah, I look forward to seeing your approach.
Yeah. Yeah, good. Thank you. I don't know that I have much of an approach. We're just going to kind of talk about the terms. I'm going to say a couple things, try to tie it all together at the end, and try to point to the things that make it so complicated within the Newtonian paradigm, as I said before. If anybody else wants to come up on stage, just raise your hand. I'll bring you up here. I'm always happy to have people keeping me honest and pointing out when I've said something stupid or that just didn't land well. So raise your hand, we'll bring you up. Okay, let's see. So let's go ahead and get started. If you'll click on the link at the top there, you see the title as usual. I just realized, Shamash, in fact, I'm going to go back and try to put links to the YouTube videos too. I'm sorry that I haven't thought to do that yet.
What links are you thinking about? Because under the YouTube video, I have always links to your folder, to the Nibbles of Physics, to your public documents, to your SoundCloud.
He
There's
means the
links
other
for
way,
everything.
Shamash.
Yeah, I just meant the other
To the
way.
YouTube.
Right. Just there should be, for people who find this first, they should know that they can watch a version on YouTube as well. So I plan to have
I
a
still
link.
don't understand.
Well, I'll have a link to the Clubhouse discussion as always, but I'll also have a link to the YouTube video. And I understand that you point back
and
at this.
on the doc itself.
On
Yeah, okay,
right.
okay.
Yeah. So that'll be coming. If you go to slide 2, we're going to get right into it. What's a pound? What's mass? What's weight? We're going to talk about some of these things. And I think one of the best ways to start is to look at the Britannica entry on what is a pound. You'll notice right away it says it's a unit of weight. That's what it says. And then it says a pound is a unit of avoirdupois weight, equal to 16 ounces, 7,000 grains, blah, 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 so many kilograms. Now, kilograms is, I think, pound is a confusing thing, as we're going to see here, but I think nobody has any question that a kilogram is a unit of what we call mass. And so here in this Britannica entry, saying that pound is a unit of weight, it is equating it to a thing that is a unit of mass. And even in England, where a pound is, I think, usually considered a unit of mass, this would be weird to say it's a unit of weight and it's equal to a thing that is a unit of mass. Would I be wrong in saying that, Ben? Oh, we could try to get you off your exercise.
No,
bike.
I'm good. No, I'm sat here. It's very, very chilled. So as a Brit who's pretty anal about these things, when I recall pound, I see it as a mass in my head as 2.2-ish to the kilo or whatever it is.
Right.
And that's it. I don't think too much further. If I was to think in terms of the difference between weight and mass, microgravity, whatever, something in a centrifuge, I would be thinking in SI terms anyway. I'd have already shifted myself into SI units. So I'd be clear whether I'm talking about newtons or kilograms. So yeah, I think the short answer is certainly I consider pounds mass. And I think most Brits don't even know the difference between weight and mass, so it doesn't matter.
Yeah, I think that's right. I've learned that actually only recently, kind of from talking to you. I hadn't realized how thoroughly the pound, which in the U.S. is a unit of force, It's a unit of weight. It's a unit of force. Is in England a unit of mass. So it's interesting to me here in Britannica, where everything in the definition suggests that it's a unit of mass, and yet it says right up there that it's a unit of weight. Now, maybe weight, is it common in Britain to think of weight as being measured in units of mass? Weight, a
yes. Yeah.
quantity
If
of
you ask
mass?
somebody's weight, they're going to either tell you how many stone they are, or how many kilograms they are.
It's interesting. That is interesting
I
because,
mean,
yeah,
people just make the reasonable assumption that local gravity is 9.8-ish.
right.
And that's about
Well,
that.
I doubt that that's
Well,
even it, right?
they're
They're
not
just
doing that in
thinking,
they're not doing that in their head. But I mean,
right.
culturally, that's kind of, we don't make the distinction between weight and mass.
It's interesting because, as we'll see, I mean, one of the things, of course, the thing we're talking about is the difference here is the kind of what we call the inertial character of mass, and then also its gravitational character. And usually when we talk about the gravitational character of mass, at least in the US, that's when we talk about weight. What you weigh is the how much force you exert on a scale or something like that. Anyway, we're already starting to see some of the confusion here, but it is fair to say that even in different countries, these things kind of have different meanings, and they are interchangeable. Weight and mass are kind of interchangeable because of the fact that we all live on Earth, where if you can specify the needle reading on a spring scale and infer that that's telling you how much stuff you have put on the spring scale. I'm kind of getting ahead of myself, I guess, even to say that. But anyway, there's the Britannica definition. Now I want to do, in slides 3 and 4, I want to talk about the Wikipedia definition of the pound, where it's a little more careful to distinguish between the pound as a unit of mass and the pound as a unit of force. Even Wikipedia does say that the pound is a unit of mass. And sometimes we say pound mass just to be very clear that we're talking about mass rather than what I would say weight or force. So the pound, as it says here, the pound or pound mass is a unit of mass used in both British Imperial and United States customary systems, etc., equating it to kilograms, etc. And we're going to talk about what mass is in a moment, but let's go right on to slide 4 to see Wikipedia entry on pound force, which is which it suggests should always be referred to as pound force or pound of force to distinguish it from the pound, which it does suggest is a unit of mass. This is all interesting to me because at least and I don't know, maybe it's changed even in the last 5 or 10 years here in the US, but in the US, introductory physics students are taught that the pound is a unit of force. But evidently these days, at least internationally, and certainly as suggested by Wikipedia, the pound is a unit of mass, but there is a thing called the pound force, which is the force that a pound of mass will exert on your hand if you hold it in your hand. It's the force that you will have to exert upward to keep that pound from falling to the ground. And if you have 2 pound masses or pounds in your hand, you'll have to exert 2 pound forces, 2 forces of 1 pound force each, or I should say, a force of twice that, in order to keep that mass from falling to the ground.
Well, only
So
on Earth, at the surface of Earth, which is where this whole topic is a little flat earthy, in that nobody really cares about the difference between force and mass, weight and mass, until it matters. And by the time it matters, you know what you're doing anyway, and then you're a scientist and you use SI units and you don't get confused. It's another one of these topics.
That's right. That's right. And maybe it's probably worth saying I've been concentrating on pound here, but I probably should have been concentrating on the Newton in the SI system, System International, the metric system as it's otherwise referred to. The unit of force is the Newton, and the Newton is and the Newton is the well, how do we even define a Newton? I guess a Newton is basically the weight of oh dear, what is it? A
The,
32nd
if
of a
you
kilogram, I guess.
yeah, if you choose G as 10, make your life easier.
Yeah,
Well, the Newton is the force that causes a mass of 1 kilogram to accelerate at 1 meter per square second, right?
that's right. That's right. So that's the way to say it. That a Newton is the force that causes 1 kilogram of mass to accelerate at 1 meter per second squared. So that's the definition essentially, and it means that a kilogram. What that means is that a kilogram has a weight, at least the way I think of weight, of 32 newtons on Earth. Not 32, of 9.8 newtons on Earth, because of the fact that it would accelerate at 9.8 meters per second squared if left to its own devices under the force of gravity. You see, I think in these first 4 slides, I've already succeeded probably in confusing. You may have come into this room thinking you kind of understood weight and mass, and now I've just made it completely opaque. So we'll try to start clearing that up here. So what is mass? Here's the Wikipedia entry on mass. It's an intrinsic property of a body. Oh, what does that mean? And usually people resort to saying just this. It was traditionally believed to be related to the quantity of matter in a body. I probably wouldn't have said it that way, that it was traditionally believed. I would just say it was traditionally described as the amount of matter. But what does that mean? What does it mean, the quantity of matter? What on earth could a phrase like that even mean? Until the discovery of the atom and particle physics, it was found that different atoms and different elementary particles, theoretically with the same amount of matter, have nonetheless different masses. Now, I'm not even sure what it's referring to here, but it may be the fact that, for instance, when I put 2 hydrogen atoms together to form a hydrogen molecule, the mass of a hydrogen molecule is actually less than the mass of the 2 hydrogen atoms that you put together to make it. And so that seems like rather an odd thing. Now, that difference turns out to be really, really small, but there is a difference. And the fact that there's a difference means it can't just be the fact, it can't be just that one hydrogen atom has a mass and another hydrogen atom has a mass, and that when you put them together, you get a molecule that has twice that mass. There's something else going on there. And the something else that's going on is related to E equals mc squared in a way that we may or may not get to. We won't get to during the discussion here, but we might get to later on. But mass is a little mysterious. It is, at least in some sense, a property of a body that doesn't require it to interact gravitationally with anything. A body has mass. Presumably, I shouldn't say presumably, by the definition, it will have the same mass wherever it is in the universe, even though its weight may be different. For instance, the mass of an astronaut presumably doesn't change because they're in the International Space Station, but their weight does. They all of a sudden they have no weight in the International Space Station. How did that happen? Are they not subject to gravitational force? Well, they're just a little bit above the Earth. They're certainly subject to the gravitational force. How does it come that they have no weight? If they have mass and they're in a gravitational field, there's something very odd going on there. That we need to get at. Let me stop there and just see if I've thoroughly confused anybody, or if any questions come up from that, from my attempt to confuse you. And once again, we welcome on
I
stage
had
if
a
you'd like to
question.
come and join us. Go ahead, Hermes.
What really brought me into this room is I believe that mass and weight are like an illusion based on the particle field. I haven't completely figured out how, but I look at like the blanket, right? And things like that. And you use the word mysterious when you described, right, mass.
Mass is mysterious. I think one of the things, if you, I don't think you can read this definition of mass in the Wikipedia entry, which is a pretty good one, frankly, without kind of appreciating the fact that it's a little mysterious. Just having to resort, even as we always did before, to saying that mass is a measure of the amount of matter. What does that mean? I mean, in what sense is mass a measure of the amount of matter? It's not the volume. You could say it's the density times the volume, but that's just begging the question, because density is the amount of mass per unit volume. And once again, you're back to trying to understand what mass is. And some of you may remember the discovery of the Higgs boson 10 or 15 years ago, which had been predicted for some time to be the particle that gives other particles mass. And everybody said, oh, yeah, okay, good. And everybody knows to talk about the discovery of the Higgs boson. They knew to say those things. But even I don't understand what that means. Ben, I saw you try to say something.
Well, I was just going to say that this caused me issues until I stopped saying mass and started saying mass energy in the same breath, like space and time caused me issues until I started saying space and time in the same breath. So that helps a little bit.
Yeah, I think it helps a lot. And I think that is worth maybe saying, even though it's not really part of what I wanted to say today. But that if you do look at mass as we have now for 100 years in physics, as just simply the amount of energy in a system in its own rest frame. The mass, what mass is understood to be, is the total amount of energy contained by a system in its own rest frame. That is what mass is. And the way you, once you've determined that energy, the way you find the mass is simply to divide it by the speed of light squared. The energy divided by the speed of light squared gives you the mass. So it does turn out to be a very useful way of doing it. I don't know that it necessarily speaks to the average person, but it is the case that the mass of a system can be converted to pure energy, if you want, or energy in some other form. And so the two things are equivalent. Go ahead, Andy.
Without going to relativistic concepts, would it be useful to define mass at, like, okay, if a unit of force was defined as that force which would accelerate a certain mass a certain amount, could you go circular on that and be like, the amount of mass is that stuff that, when a certain force is applied on it, you get a certain acceleration. So it's defined in its inertial terms, stuff that resists acceleration.
Yeah,
without thinking about gravity at all.
That's right, and as we'll see in a moment, that is actually maybe the purest way to measure mass is in terms of its inertial characteristics. It's not the way we measure mass with any of the ways that we do measure mass, where we have scales to measure mass. All of them rely on there being a gravitational field to work, as we'll see. You were saying something at the beginning that reminded me one of my favorite papers, a paper by a guy I knew named Robert Weinstock, who wrote a paper for the American Journal of Physics called F equals ma. What is F? What is M? What is A? And kind of succeeded in kind of showing that the equation F equals ma is probably best seen as a definition of force, because it really comes after. You have to really understand mass and acceleration before you can understand force. You can think of it as, if you understand any two of those, then you can define the other one in terms of the other two. Acceleration is pretty easy to understand, just kinematically. But mass and force kind of share the same fundamental mysterious character, in that you have to get to the bottom of at least one of them to understand the other one. and it does have to do with the inertial characteristics of mass, which I think ultimately is the point of the Higgs boson, kind of giving things inertia, resistance to being accelerated. So, okay.
Can I just add a quick
Yeah, go
thing
ahead,
here?
Shamash.
Just 2 words, because in the Newtonian universe, all of a sudden there's this mysterious being appears, which is the force. Just to comment on Hero's comment here, this force is, and he says F is equal to ma. And before this instance, M has absolutely no definition, and F has absolutely no definition. And the traditional way we solved it was, and I'm sure John will mention it at some point in his presentation, we had the kilogram, like we had the mass, and you just divided that, right? And so once you define the mass with a physical object, then you can get the force, which is this metaphysical being that is whatever you do to push something. It's a number that helps the equation work.
Right. One way to think about force is to think about a spring, for instance, and the fact that when you stretch a spring, there's clearly, it takes more of, just conceptually, clearly it takes more something to stretch a spring by more than less. And in fact, there are ways to determine that a nice spring takes twice as much force to stretch by twice as much, and so on, that it's a linear thing. So a spring is a nice way to kind of define force if you want in that way. You have to come up with some way of determining how it is that you know you're applying twice as much force to it. And maybe the simplest way to do that is just hang two identical things from it. But now you're talking about gravitational force and mass again. So I don't know if any of that lands, but there is a circularity in F equals ma. One of the F and M in particular, it's not clear which one comes first.
Another quick thing,
Go ahead.
John. If anyone's been listening carefully, you said that 2 hydrogen atoms separately have a slightly lower mass than 2 hydrogen atoms combined into a molecule, I think.
Slightly larger, yeah.
Yeah, separately they have larger than the combined, yeah. If I said that backwards, sorry. But then you
Right.
also said that mass is the total energy of a system when viewed in its rest frame.
Right.
So those two, they do reconcile, but it
But
just...
maybe I should.
Well, no, it's just that if anyone's listening carefully, they don't seem to reconcile. And it goes back to our constant discussion about making sure we're careful about what the boundary of the system is, right? I mean,
Yeah, right.
I don't know how you want to put it across. We know it's as the bond forms, the energy is released out of the system, and that accounts for the difference in mass. But I just, if anyone's listening carefully, they'll notice that discrepancy.
Yeah, no, that's right. And this may be worth, as you say, maybe another word. The point is that to create 2 hydrogen atoms out of a hydrogen molecule, you have to put energy into the system, because a bound system is a system that is bound precisely because it doesn't have enough energy to be unbound. So if I want to make 2 hydrogen atoms out of a hydrogen molecule, I have to put some energy into that system. And when I do that, I'm putting mass into that system by virtue of E equals mc squared. Yeah. Okay. Yeah. Anything else, Penn? Okay. Yeah. So let's move on to 7 and talk. I'm sorry, not 7. Where was I? I want to talk about weight. Yeah. First of all, so the Wikipedia entry on weight. What is the weight of an object? And here, especially the second paragraph there, if that doesn't confuse you, you haven't read it carefully. Weight is a funny thing because, of course, we say, it's what a spring scale measures. Oh, it's the gravitational force on an object. It's a vector, and the weight is a force. It's a force, and therefore it's a force that happens to be down, kind of by definition, because that's the direction of the gravitational force. But all of those things are a little odd too, because in fact, when we step on a scale, the scale is not measuring the gravitational force of Earth on us, because the Earth is spinning. And in spinning, it tends to throw us off. It doesn't spin fast enough to throw us off, but it does spin fast enough to reduce the the net force with which we're attracted to Earth. The scale doesn't know that the Earth is spinning. All it knows is how much force we're applying to it. And the force we apply to it depends on other forces that are acting on us, which include that centrifugal force and the actual Newtonian gravitational force, if you want. And we'll get back to this later. But it's impossible to separate out those two things. All a scale can measure is how much force we apply to it, right? You can stand next to a bathroom scale and push on it with your hand and make it show the force that you're pushing on it with. We assume that when we stand on a scale, we're pushing on it with a force equal to the force that the Earth exerts on us. But that's true in a sense if by the force that the Earth exerts on us, you mean the force that it exerts on us when we stand on the Earth. But it's not if by that force you mean the gravitational force that the Earth exerts on us, because we can't measure the gravitational force that the Earth exerts on us because it's inseparably mixed with the fact that the Earth is spinning and therefore producing a net force on us that is convoluted with the centrifugal force, which is trying to throw us off of the Earth. And that's where a lot of the confusion begins. So what does it say? Some standard textbooks define weight as a vector quantity. As I was saying before, it's the gravitational force acting on the object. If it were, then that force would be toward the center of the Earth. But the force that we call our weight actually doesn't point toward the center of the Earth. It points slightly, if we're in the northern hemisphere, it points to a point on the axis a little bit below, a little bit south of the center of the Earth. The Earth is an oblate spheroid for that reason, once again having to do with the centrifugal force. Others define weight as a scalar quantity, the magnitude of the gravitational force. Yet others define it as the magnitude of the reaction force exerted on a body by mechanisms that counteract the effects of gravity. The weight is the quantity that's measured by, for example, a spring scale. Okay, that's true enough. That's certainly what we always say. A spring scale measures your weight. And yet, once again, it's not measuring a gravitational force, as we will keep continuing to talk about here. And et cetera. It goes on and on. There's a lot of confusing stuff there, and we're going to try to get to the bottom of that in the next few. So let's just go on to slide 7, look at a few spring scales here. These are examples of spring scales, a bathroom scale, a fish scale, and even a doctor's office digital scale. We've all been to doctor's offices showing a beam scale, which we'll get to on the next slide. But this is an example. A digital scale is actually just a glorified spring scale. All of these scales work in the same way. They measure what I would call a force that is applied to them. In the case of a bathroom scale, it measures the force that you push on its surface with. And one way to push on its surface is to stand on it. You could put some boxes on it. You could stand on it carrying your dog and then not carrying your dog and subtracting to find the weight of your dog because your dog's not talented enough to stand on the spring scale all by itself. You can do all those things, but we all kind of know intuitively that it's measuring how hard we're pushing on it. A spring scale does a fish scale does the same kind of thing, except in some sense, a fish scale is stretching a spring maybe, whereas a bathroom scale maybe is compressing a spring. Not necessarily. You can build those things so that they compress or stretch a spring. Maybe I should take a moment to say, consider a fish scale. That fish scale has a hook down there. When you put a fish on it or any other kind of a weight, it pulls on that thing. A little indicator, as shown there, comes down the side. And it may be that you're stretching a spring that's actually suspended from the top of that compartment. But it may also be that you're compressing a spring that is attached to the bottom of that compartment. So you don't know whether you're actually stretching a spring or compressing a spring, but you are causing a spring in some way or another to be longer or shorter than it was at the beginning. And all the spring scale is doing is providing a readout of how much it has done that. In the case of the digital medical scale, it may be, I don't know how that works, but there are things called piezoelectric crystals that will put out a voltage equal to how much force you're compressing them with. So there are lots of ways you could do this, but all of these things are measuring a force applied either to a hook or a platform, and then in the last case, converting that to a digital readout. It is measured, but they're all really directly measuring forces. Benjamin, I see your hand raised. Did you want to say something? Maybe it's...
Yeah, I wanted to make an interesting point. I wanted to argue that
well, just try.
a spring, a spring scale does not measure the same thing as a balance scale. And to support this claim, I want to take you on a little rocket ride to Mars. You're going to go to your doctor. You're going to pick up the spring, the balance scale at your doctor's office.
A balance scale or a balance and a spring scale.
A balance scale
okay.
From your doctor's office, and the spring scale in your bathroom. And we're going to take you and me, go to Mars, and you're going to get out on Mars, and you're going to stand on both of them. Now, here's what I predict. On the spring scale from your bathroom, you will weigh, I don't know, like a third of what you weigh on the Earth. But on the balance scale, you will weigh exactly what you weighed in your doctor's office.
Excellent. Thank you so much. I almost feel like I've paid you or something. You're making a point. Oh, I see Ben actually disagreeing with you. Maybe we'll get to him in a minute here, but you're making a point that I intended to make actually with the next slide and the slides after that. So thank you. That was a nice presaging. Ben, did you disagree with something there?
Well, I won't disrupt the flow anymore. Just carry on to the moment, but I'll explain why I put the X a little later if you haven't already.
Okay. Maybe it's a subtle point or something that I missed in what Benjamin said. But let's to see what Benjamin said, let's move on to slide 8, where I have a variety of balance scales. Balance scales like this don't measure force directly. There's no springs involved. They are comparing the weight of one thing to the weight of another. So in the purest form, just a simple like that one up there in the upper left, just a balance scale. You put some stuff in one pan and you put stuff that has a known mass in another. And if it balances, then you say the two masses are the same. And usually we use scales like this to measure mass, we say, rather than weight. And there's a reason for that related to what Benjamin was talking about. In the purest form, it's really simple there. I have some standard weights, a kilogram, tenths of kilograms, hundredths of kilograms, grams, millikilograms if you want. And I can put them in one to know how much mass I have on one side and then see how much of that it takes to balance something on the other side. If I want to measure out a kilogram of carrots or something, I put a standard kilogram on one side and I put carrots on the other until they balance, and then I know I have a kilogram of carrots. In its less pure forms, we have these triple beam balances and medical balances like the one at the far right over there, which are once again comparing weights, comparing downward forces, but now over a lever. Basically, you have a seesaw kind of an arrangement, and you're taking advantage of the fact that if you move a small weight further from a lever arm, it will provide more torque more torque on that side. So what you're really doing is comparing torques, turning moments about a lever arm of some kind. So all of these are doing that, and I asked in both cases, would these things, do all the spring scales measure the same thing on the moon? Would they measure the same thing in the ISS? And I should have answered that question. If we go back to slide 7, as Benjamin was saying, these scales would not measure the same thing on the moon because we say because gravity is not as strong. That's in the Newtonian paradigm. We would say because gravity on the moon is not as strong. So they would measure on the moon something like a sixth of what they measure the thing to be, the weight of the object to be on the Earth. But they would work. They would give you the weight on the moon. It would be different from the Earth, et cetera. They would work. They measure the same thing in the sense that they both measure weight, but they don't get the same value because they're measuring weight, not mass. Whereas on slide 8, these balance beams would measure the same thing on the moon because they're just comparing the weights on the two sides of the fulcrum. And if those two things have the same weight, then it says they have the same mass. And this is why we think of these things as measuring mass, a thing that is independent of where the object is. But what about in the space station? If I tried to measure the weight of an object in the space station with a spring scale, it wouldn't work. What about mass? If I tried to measure the mass of something in this International Space Station with a balance beam, it wouldn't work. I would not be able to use either of these devices in the space station. And that's a little bit of a conundrum. One is measuring weight, supposedly gravitational force, if you want. One is measuring mass, which is related. It has to do with gravitational force. But why can't we measure the mass of something in the International Space Station? Well, we can, but we can't use any of these devices to do so. Benjamin, did you have a follow-up, or anybody else have a follow-up, or do you want to say anything about all that?
I think Ben has already explained how you measure mass in the space station. You use a balancing system, but just take, for example,
that's not a balancing system, yeah. But go ahead.
I've never said that.
I don't think he said that here.
I would object also to John that you can't measure mass with these things in the space station. I think you can, but you have to put them in a centrifuge.
Oh, that's fair enough. That's true. Good point.
Float them, like if two people, well, if you have a known weight, take kilograms of equivalent to your own weight, something like it, in some decimal value, nearest value, and then connect yourself to it with a rope, and then get yourself into a kind of a dancing spin with that kilogram, and have somebody else watch the point on the rope that is not moving. That will be the balancing point between the two of them.
Someone's been reading Hail Mary.
Wait, what did you say? Reading Hail Mary?
Hail Mary, yeah.
Hail Mary. Yeah, but I think it's about the simplest way to do this.
Yeah, no, that's fair enough. And Ben's right, and you're right too, Benjamin, that you can use these devices, but you then have to put them into an environment that is accelerating somehow to generate an artificial gravity. All of them depend on there being some kind of, quote, gravity, unquote, in order for them to work. And that gravity can just as well be, quote, artificial as, quote, natural. I don't like to make a distinction between artificial and natural because they are, in fact, the same thing in relativity. But that's a good point, is that one can use these devices even in outer space as long as you do put them in an environment that itself has an artificial gravity. Which I think is what both of you are saying. Yeah, go ahead.
Just a small comment. I'm very quickly. First of all, this discussion is very relevant to the philosophy of the scientific method, or you want to call it philosophy of science, where we gave this example in an earlier room of the Philosophy Wednesdays when we were talking about operational definition. Are you measuring the same thing when you switch the device? So is it a balance or one of those dynamometers, the device with the spring? Are you measuring the same quantity, yes or no? And I kind of heard you, John, use both. So you refer to the dynamometer as measuring directly the force sometimes. I don't believe this is the case, because if you were to be very careful, and I think you noted this during the presentation as well, that the dynamometer is only measuring displacement. It's measuring the compression or the expansion of a spring, and then the formula translates it to what the force is. And then the Robert-Farr balance, the balance that compares the two masses, it's also measuring that, but then the formula also converts it to newtons. So in both cases, this force entity is not something that you can directly observe. You're gonna measure it with some other observable quantity and then go back and find the number.
Right. I shouldn't have used the word directly when what I really meant is that it fundamentally is more what I meant, right? A spring scale fundamentally measures a force, whereas a balance fundamentally measures a mass, but it does so in kind of a funny way. It does so by comparing gravitational forces, and that gets at even a more important distinction, or a more important point, which is this so-called equivalence of inertial and gravitational mass. When we talk about the mass of an object, if the gravitational force on a certain amount of gold is the same as the gravitational force on a certain amount of feathers, then the inertial mass of the gold and the inertial mass of the feathers are the same. That's weird. That in Newtonian mechanics, there's no explanation for the equivalence of the so-called gravitational mass, how much something weighs, with the inertial mass, how much something is resistant to being accelerated. And that comes very easily in the relativistic view. Go ahead, Ben.
Just to say, of course, a feather's a terrible example on Earth because
Yeah.
the massive effect of air resistance, but yeah, like a lead ball or something.
How about a pound of feathers or a kilogram of feathers compressed to the density of gold? How about something like that?
That'd do. It'd be almost like using gold as the example.
It would be almost like using gold. That's right. Okay, let's see. Anything else? All right. Well, let's move on to 9. How do they actually measure? Astronauts are on the space station for a long time. They like to kind of keep medical records, et cetera, see how their weight is doing, even though they have none. Of course, what they mean is how much of this astronaut is there 1 month after this astronaut was put in space. And what they really want, what we almost always really want when we measure weight is mass. That's really what we're looking for in almost every case. And the way they actually do it on the International Space Station is to really literally make what I would call a measurement that is fundamentally about mass, much more fundamentally even than in a balance beam, which relies on weight to measure mass. Here, they have a device, and there's a video there you can link to, you can watch if you want. Guy gets on this piston, which is connected to a spring, and releases it. Somehow it's driven. I don't know exactly it has to be free to oscillate somehow, but it must be driven at least at first. I don't know exactly how it works. But fundamentally, the idea is you attach the astronaut to the end of a spring, and then you compress the spring and release it, and the astronaut oscillates up and down with a period that is determined by how strong the spring is and how massive the astronaut is. The more massive the astronaut is, the longer it will take for the astronaut to go through one up and down, whatever, back and forth cycle on this spring. And you can calibrate that. You can either calculate it directly from first principles, but I'm sure that's not what they do. They simply calibrate it by putting different masses on it, knowing how the period is related to the mass, and then reading the mass directly off of the period of oscillation. Now, it's interesting that in doing this, the astronaut has to has to be as kind of as motionless as possible. The astronaut has to connect himself to as kind of the end of this spring-loaded device, and then just hold on. It won't matter a lot if the astronaut moves a little bit, but the astronaut could screw up the reading by kind of pumping. If they wanted, if they pumped like on a swing, you could change that period of oscillation at least briefly. And screw up the reading. So it's really important. The device has a couple of things to put your feet in, to hold on to, and then I'm sure the instructions, even though he doesn't say it, the instructions have to include just hold still. It's not a fast oscillation, so it's not like it wags you back and forth in any way that's difficult to do this, but you do need to hold on and try not to move very much while you're oscillating back and forth, up and down, whatever you want to call that. It looks like up and down in this video, but that's just because of the way the camera is mounted. So anyway, and I think you can understand that if you imagine just attaching a mass to a spring. The bigger the mass is, the longer it will take to oscillate, just because of that inertial resistance. Go ahead.
Yeah, I just remember speaking to Story about this. Story Musgrave. There were two competing systems. One was using a spring and looking for the natural frequency, and the other is you just use like a hydraulic or pneumatic piston and force sensors, and then you induce an acceleration and see what force is required. And they went for the latter. They went for the spring because it's mechanically simpler and produces less vibrations that upsets less other instruments on the space station, etc.
Right. And I think I just learned this morning, evidently, at least the American system was that just hydraulic force, a linear accelerometer, essentially. I think this oscillating system came from the Russians originally, if I'm not mistaken. I don't know if you heard any of that story.
No, I was just talking about like why would you do it one way or the other? And it was the simplicity and the lack of vibration that made this spring win over.
I was surprised because I just thought this was always the way they had done it. And then at least something I read suggested that the Americans had been using this linear actuator. And the Russians came up with this thing, which struck me as kind of the most obvious way to do it. Andy, go ahead. You had something to say?
Oh, I was just imagining somebody proposing that. Well, this would be like the worst idea for weighing babies in a maternity ward.
It sounds like a Far Side cartoon, right?
Don't shake the baby.
Yeah. Okay. So at any rate, so we've talked about mass and weight, different ways of measuring them. Hopefully all that's pretty clear, the difference between balance beams and scales. The fact that balance beams do depend on there being some kind of an effective gravitational force, because they're really comparing forces, ultimately, comparing torques, if you want to think of it that way, in the triple beam balance scale kind of a way. But clearly they're kind of fundamentally based on different things. A spring scale is fundamentally about the force, whereas a balance beam is fundamentally comparing masses through the forces on those masses. And then, of course, the International Space Station, which is really, I mean, you can see how difficult it is to really measure the mass of an object. You would never have one of these devices in your home. It's too bulky. It's so much simpler to essentially either use directly forces or compare forces, as all of our earthbound scales do. So does weight equal the force of gravity? Let's talk about that for a second. This is a nice diagram I found on the web, and I wanted to just put it here because it shows a little bit about what's going on when we stand on a spring scale on the Earth. First of all, you probably know that the Earth is an oblate spheroid. It's slightly bulged out at the equator because it spins. As it was forming, it comes to a shape that is fundamentally everywhere perpendicular to the gravitational force. If the surface of the Earth weren't perpendicular to the gravitational force, then of course stuff would tend to roll along the surface of the Earth. And that's essentially what has happened. It was spinning, stuff rolled out or mushed out, however you want to say it, toward the equator until it was a shape such that the gravitational force was everywhere. I say gravitational force, I should say the effective gravitational force is everywhere perpendicular to the surface of the Earth. And that means, and that's what is shown here, all of those green arrows are the effective gravitational force. When you stand on a scale, you're standing vertically upward. Those green scales are perpendicular to the surface toward inward, or I should say inward, they're clearly not toward the center of the Earth. The green arrows in the northern hemisphere point to a place below the center of the Earth on the axis. The green arrows in the southern hemisphere point to a place above the center of the Earth on the axis. And that's the result of the centrifugal force. All of the red arrows are showing the centrifugal forces on that would appear at different places. When you're on the equator and you're a long ways away from the axis of the Earth, rotating about it once a day, there's a certain outward centrifugal force that reduces the gravitational force shown in blue to make an effective gravitational force shown in green that's a little smaller but in the same direction. So on the equator, at least, you're standing perpendicular to a surface such that that perpendicular goes through the center of the Earth. And the effective force on you is a little bit less than it would be because of the centrifugal force, which you have to add the red force, you have to add to the blue force to get the green force. Now, that red force is shown much larger than it really is. The centrifugal force is, I think, a few tenths of a percent of the gravitational force. So those things are wildly exaggerated there. The green arrows are not very different from the blue arrows, but they are different in the way shown. You'll notice that the red arrows get shorter and shorter as you get closer to a pole, because at those latitudes, you're still going around a circle once a day, but you're now not going around as big a circle. The centrifugal force gets larger in direct proportion to how far you are away from the axis. Anybody who's played on a playground merry-go-round as a kid knows that you can stand at the center of the merry-go-round with no problem. You can step out a little bit, and there'll be a little bit of force kind of pulling you out. But as you get out further and further, that force gets pretty large. And if you spin that merry-go-round fast enough, you might not even be able to hold on at the outer edge. You might actually, get thrown off, because they're the only force keeping you from being thrown off is how hard you can hold on to whatever rails they have, or how frictional your shoes are, or something else. Otherwise, you will get thrown off. Let's see. So, yeah, go ahead.
Just a quick question, just to be clear, this red effective gravitational force would not exist if the Earth wasn't rotating, right?
The green effective, is that what you mean? The red,
yeah, the green. So without the red, the green would not exist. It would be only the blue, pure gravitational downwards, the normal one.
Right. Without the centrifugal force, the green force would be the same as the blue force, right? The effective gravitational force would be the gravitational force.
I'm not sure how you're saying. I'm not quite sure how you're saying centrifugal force without going afterwards. That's all.
Without going what?
Spitting. Maybe my AirPods are blocking out me making a spitting sound.
Gagging.
Some sort of visceral reaction to the word centrifugal.
Oh, you mean because physicists are supposed to say there's no such thing as a centrifugal force? Is that what you mean?
I actually think it's quite elegant, as long as I think it's all fine. But I was slightly surprised to hear you having no nervous system breakdown.
Oh yeah, no, I was subject as a student to teachers telling me there's no such thing as a centrifugal force. There's only a centripetal force. It's the centripetal force, the force toward the center, that makes things move in a circle and all that. And all that's fair enough. But I actually, as a teacher, I found a little diversion now into pedagogy, I guess. If I ever used the term centripetal force, the force that makes something move in a circle, that was always followed by students on exams when they're trying to find the forces acting on an object. They would say, okay, well, for instance, if I'm whirling a rock on a string around my head, so I'm whirling this rock around on the end of a string. There's a gravitational force on the rock pulling it down. There's the string force pulling kind of up at an angle and inward. And then, because it's moving in a circle, then there's the centripetal force, mv squared over r, toward the center. And they would add those three forces to get the net force on the rock. This is always what would happen if I ever talked about the centripetal force. And so I was always careful to point out that forces, when you're analyzing a system, you look at things that touch the system. And if there's nothing that touches the system, then it doesn't exert a force on it, with one mysterious exception. Gravity is the one mysterious exception that exerts a force on a system without the need to touch it until we get to electricity, et cetera. There's other forces like that. But at least in introductory physics, gravity is this weird force that acts without the need to touch. And I tried to emphasize that and then doubly emphasize it by not talking about centripetal forces, so they wouldn't think there was some other force that arises because an object is moving in a circle. Things move in circles because the real forces acting on them add up to a force toward the center, which is what you can call the centripetal force. But centrifugal force is a real thing. When we stand on the Earth, if you don't think centrifugal force is real, then you don't think that it has anything to do with the reading on a scale, but it has everything to do with the reading on a scale. It is in there. It's a real thing that has real consequences for our everyday life, just like the Coriolis force does. That's another real force that has real consequences. And general relativity only comes along and makes this clearer because it relegates gravitational force to the same category as centrifugal force and Coriolis force. Any force that depends on the mass of an object is an inertial force. A so-called fictitious force, if you want to call it that, doesn't mean it's not a real force. It just means that it is a result of analyzing in a non-inertial reference frame. Sorry, that was a long spiel, but go ahead, Ben.
Yeah, so when I go around a roundabout in a car, I don't like to think about a centrifugal force pushing me outward. That feels completely at odds with the simple idea that bodies like to continue in how they were moving unless they're acted on by a net external force. I like to think about the fact that the reason I'm going round the roundabout is the car is pushing me towards the center of the roundabout. And they are somewhat compatible, but they're almost opposite ways of looking at it. So how does that reconcile with what you just said?
Yeah, so I guess the only thing I would say there is the interesting thing about that, of course, is that what it does require is understanding that the thing that we experience as a gravitational force, and we really literally experience a downward gravitational force when the only force acting on us is an upward force. And that's a weird psychological thing, right? When we stand on the ground, there is, according to the current paradigm in physics, exactly one force acting on us, and that's the force of the ground on our feet. That's an upward force. And it makes us experience a downward force, which we call the gravitational force or our weight or something like that. And that's a weird kind of a psychological thing. And the same thing happens in the car, right? You can think of it in terms of what you think you feel. If you don't think about it very carefully, I think most people would say, oh, I feel thrown out toward this door, right? And yet, if you think about it carefully, you'll realize that the only thing you're feeling is a force that is making you turn to the left or turn to the right. Go ahead.
Well, it's obviously plastic in the mind then, because I don't think of being any downward force of gravity. Maybe I've just thought about it too much. I always
Yeah.
think about what's pushing me upwards and accelerating me upwards. So.
I think it happens more. Maybe it's better if you get in a Tesla and step on the accelerator pedal in insane mode. I've done that once or twice, and you
I have
feel
a quick
pushed
question
back
for
into
you.
your seat. Yeah, I'll get to you in a moment here, Hermes. When you feel pushed back into your seat, I think that really feels like, I mean, if you close your eyes and kind of forget about what you're seeing out the windows and everything like that, that really does feel like a backward force, pushing you into the seat. And yet, obviously, the thing you're really feeling is the seat pushing on you in the forward direction. But anyway, not to beat a dead horse. Go ahead, and then we'll go to Hermes. Go ahead,
No, I
Ben,
was just
first.
literally going to say, but it doesn't have to. I see it as the car coming and slamming me in the back, coming up to me and
Yeah,
pushing me in the back. So you can change the way you feel about it. I literally realized from what you're saying, I think completely differently about it.
yeah. Well, I think
Yeah.
about it both ways. I think it's helpful to understand both viewpoints, and I think people do in different situations kind of see it differently. Go ahead, Hermes.
Yeah, I just quickly wanted to say that, like, the way you explained it, just confirms for me that up, down, right, the directions in that way, forward, Ben talked about forward, is really like an illusion.
I mean, I think that is a really important point. A lot of people think that down is something that pre-exists before gravity. That's nonsense, of course. Down is, by definition, the direction that we say gravity is. And one consequence of that, of course, is the fact that since down is not toward the center of the Earth, it can't be the gravitational force. It's something that we experience in our reference frame. Down is the direction that an object falls, and objects do not fall toward the center of the Earth. They fall in the direction of what we call local gravity, which is not the gravitational field of the Earth. It's the combination of the gravitational field and the centrifugal field, if you want. That's it can seem dogmatic at some point and maybe unnecessary, but I think it ends up clearing up a lot of confusion when you start doing this. We'll get to the GR perspective here in a moment. Okay, so I think so as I said, what is down? Why is the Earth? The Earth is oblate precisely because down has to be perpendicular to the surface of the Earth unless you're standing on the side of a mountain or something. Down is the direction that perpendicular to a level when the bubble in the little bubble level is in its appropriate little, level spot there. That's what down is. And that's just the direction. It's the direction something would fall, and it is not the direction of the Newtonian gravitational force on an object, for the reasons that we've been beating with a dead horse, beating the dead horse with. Okay, so let's just to kind of finish this up. If weight were the force of gravity, or even if it wasn't, we'll just ask this: would your weight change if you were on the moon? I think most people would say that your weight does change on the moon. And they would probably be comfortable saying that it's because the force of gravity is different. You're on a body that has smaller mass. The Newtonian gravitational field of that body is smaller, and therefore you weigh less because of that. And that all seems kind of nice. And maybe to the extent that I can forget about the centrifugal part, and it's much easier to forget about the centrifugal effect on the moon because it rotates once every month and it's much smaller. So there's very little centrifugal correction on the moon. So that's fine. But what about in the ISS? Most people would say people are weightless in the ISS, but they're just 400 miles away from us. They're in the gravitational field of the Earth. There's no question about that. How can they be weightless if they're subject to the same force of gravity we are? And it's not quite true. Gravity is about, Newtonian gravity is 5 or 10% less at ISS altitudes than it is on the ground. But fundamentally, they should still weigh pretty much what they do, but they don't. They're weightless, and they really are, right? Nobody would question the fact that they're not. Nobody would question their weightlessness, even if they might say, "Oh, but there is a force of gravity on them." So, is weight the force of gravity? I think most people would say, no, it's different. Somehow, weight is not the same as force of gravity in the ISS. What if the Earth stopped spinning or started spinning faster? And I think we've talked about that too. If the Earth stopped spinning, you would weigh more. Not much more, but you'd weigh more. And if it started spinning faster, you'd weigh less. But that would have nothing to do with the force of gravity, at least if you think in terms of Newtonian gravity. So Newtonian gravity wouldn't change, but your weight certainly would if that were the case. If you're in an elevator starting to move upward, now here's a place where you probably would say, I think we've all felt in an elevator when it starts, especially a fast elevator, when it starts moving upward, we feel heavier for a moment. But we would all say, oh, I know, I'm not really heavier. It's just things pushing on me hard, get me going upward. Maybe we wouldn't even think of it that much, but we'd know from experience that that's what happens when elevators go up. They have to push on us for a moment to get us moving. We feel pushed to the floor more. We feel heavier. A scale would read that we weigh more. But there's no question in most people's minds that our weight hasn't really changed. And they might say that's because the force of gravity hasn't changed. But I'm trying to kind of paint the picture here that in all these different situations, we have different rationalizations for what's going on. In some cases, the force of gravity is changing. Some cases it isn't. Sometimes our weight changes. Sometimes it doesn't. But they're not linked very well. If you're in an F-15 making a 6G turn, no, your weight doesn't change. You're just making a 6G turn. You feel heavier. A scale would read that you're heavier, but you're not heavier. The force of gravity hasn't changed. This is just you in a car going around a corner, a really fast car going around a corner really fast, etc. Hey, Steve, welcome to the stage. Did you have a question?
Yes. Good morning, John. Good morning, everybody. John, you brought up the ISS. Can you talk a little bit about artificial gravity? Because I've seen it. I'm sure we've all seen it in the movies. Is that a real thing? Is it possible now? But can you talk about artificial gravity and like the ISS? Thanks.
Yeah, well, we talked about that a little bit a while back when we were talking about using scales, that you could actually use earthbound scales in the ISS or in any kind of a space vehicle if the space vehicle itself were rotating, or if the space vehicle were just simply accelerating. If it could just fire its rockets, you could generate what feels like gravity within the bounds of that rocket. And within the general relativistic paradigm, that's the same thing. It's not artificial gravity, it's just gravity. And that's one of the points that I'm trying to make with this presentation ultimately, is that gravity in the general relativistic paradigm really is what happens when you're in a reference frame such that things that have no forces on them accelerate. I'm going to make that point in a couple of slides. But maybe the quick answer to your question is just that my view, and I think a profitable view, is to understand that artificial gravity is nothing more than gravity. There's no artificial about it.
Thanks, John.
Okay, yeah. So let's move on. Oh, let's see. We haven't quite finished here. Oh, the last two are maybe the most important. What if you were in a rocket ship firing its rockets in deep intergalactic space, generating this artificial gravity that Steve was just talking about? So if you were in a rocket ship, kind of a cartoon rocket ship, it's firing its rockets, you're standing on the floor of this rocket ship. Maybe it's firing its rockets so that you feel just like you do on Earth. You're standing there, you hold a weight, and you're holding a barbell. You're getting your workout because the barbell weighs stuff just like it does on Earth. Because the only way you can lift that barbell is to take the force that the floor of the rocket ship is exerting upward on your feet and use that force, to stand up and to hold onto the barbell, and then to lift the barbell off the floor so that you're exerting the force that makes it accelerate rather than the floor of the rocket ship being the thing that makes it accelerate. It's the same feeling you have. Is that a force of gravity? Or do you have weight in that situation? You're in deep intergalactic space. Presumably there's no force of gravity, but you clearly have weight in the sense that you could stand on a scale. Everything feels just like it does on Earth. You can make up your own mind as to whether you think that's real gravity or not. But does your feeling about that change if I take that exact same rocket ship, firing its rockets in exactly the same way, and I just place it 10 feet above the surface of the Earth, so that now it's still firing its rockets? The reason you feel that force on your feet is because the rocket ship is pushing up on your feet, but the rocket ship and you and everything in it are just hovering 10 feet above the surface of the Earth. It's the same situation, except there's an Earth nearby. And you might want to say, well, in that situation, there's real gravity happening, and the rocket firing is just providing a platform that could have been provided by a stool or something. You could be standing on a stool. And I would say, well, yeah, you could be, but you're not. You're in a rocket ship that is making artificial gravity by firing its rockets. And now you want that artificial gravity to be the same as the real gravity experienced by somebody who is standing on a stool 100 feet away outside your rocket. What's the difference between those two things? That's one of my favorite kinds of examples. And I think if you think about that example for a while, you'll start to kind of really appreciate that there's something very deep going on in that example.
Of course, there is a difference, though.
Yeah, what's the difference? Oh, you're going to talk about the tidal effect? Go ahead.
Yeah, is that what you call it? There's a great. So the difference is, if you had a scale at the bottom of the rocket and the top of the rocket, if you're actually in space and accelerating, they would register the same. But on Earth, you could actually, I mean, not just like in principle, you could actually measure the difference between the top of the rocket and the bottom of the rocket with a sensitive accelerometer.
Yeah, that's right. So there wouldn't be any difference in the reading on the scale, or at least I should say you could make it be such that the reading of that scale would be the same. But if you were to measure the gravitational field at different places in the rocket ship, you would find that in the case where it's just hovering above the Earth, it's a little bit different at the top. It's a little weaker at the top. The direction is a little bit different out to the sides, etc. And all of these things have to do with the fact that in the rocket ship in outer space, the effective gravitational field is the same everywhere around the rocket, whereas in the rocket ship on Earth, the gravitational field is a little bit different at different places. But this is why we use the term local. The local gravity, the gravity at a point may be the same, but the gravity at different points is going to be a little bit different. And this is what's called the tidal effect. The fact that as long as I limit my exploration to a sufficiently small region around some point, there's no way to distinguish between pure artificial gravity, if you want, acceleration, and real curvature of space-time is what general relativity would say. Real gravity, which includes a tidal effect. In general relativity, there's no such thing as a gravitational force, but there is such a thing as a gravitational stress. Maybe that's the best way to put it. When you exert gravity on an extended object, because the gravity at different points in that extended object is slightly different, it gets subject to spaghettification, There's a force that tends to stretch it along the direction of gravity, and a force that tends to compress it perpendicular to that. So that is an important point, but it doesn't change the fundamental fact that there's no such thing as gravitational force in the sense that we always think of it in Newtonian physics. I think the way to think about it really is that there's still a stress, and the only thing there is the stress. Does that language help at all?
Yeah. No, I can I tell you why I know this? I helped. I almost trivially helped somebody kind of design and build a drone. They came to me, they're like, I want a drone that can lift 250 pounds. And I was like, shit, that's a big drone. But they did it, they built it. They wanted to measure, they were going to lift this gravity meter to do like gravimetric
Oh,
surveys. And I was like, you know, and I was thinking about this exact thing. I'm like, well, drones are always moving around. How do you know what's the Earth's gravity and what's because of your little accelerations? And it dawned on me that the way to do it is to have two of them and have them stacked vertically, and then therefore you can measure that gradient and know that is only because of the Earth's gravity, where the up and down accelerations are from the movement of the drone are always going to sort of be the same, and then you can cancel them out. So anyways, that's the way they do it. They have an array. Oh, I think just two, at least two, very sensitive, and it's only like 10 centimeters apart too. So I
so
was
two
shocked
two
that
two gravimeters vertically separated by 10 centimeters.
Yes.
Yeah.
Yes. I was like, oh my God, it would have to be like 10 meters or something crazy. But it
Yeah.
wasn't. That's how sensitive I think it comes down to the clocks actually, because the clocks slow down when they're
Is
just a
that what
little
they're
bit.
doing? They're
I think
not atomic clock
I think
based,
so. I
are
never
are
really
they?
got a good answer from
Wow.
that part of it, but I learned that was at least the principle that they were exploiting to measure, yeah, the difference in the Earth's gravitational
So
field as you move around.
that's actually kind of amazing to me. So I mean, you think that it was maybe based literally on the general relativistic time dilation correction with altitude.
Yeah, I'm not super sure about that part of it, but I
Yeah,
might
I'd
be
be
lunging a
interested.
couple ideas. But
I know they've
the
gotten
basic
pretty
idea
good.
was,
Yeah.
it didn't seem like a thing that would have even been possible, but they did it.
Yeah, and the 250 pounds came from the fact that atomic clocks aren't lightweight, I guess.
Well, I mean, the whole, I mean, yeah, it was pretty. They had to lift. The thing is, this isn't even unique. They've been doing this kind of stuff in aircraft for decades. It's just that to get the device small enough
Yeah,
to be able to be lifted on even a large drone was, I think, the challenge.
that is pretty cool. Yeah, thanks for that. Okay, so let's see. Getting toward the end here, slide 12. Then, so what is this thing we call G? And there is a thing called standard gravity. It's defined as 9.80665 meters per second per second. That's an acceleration of 9.80665 meters per second every second. That would be the rate at which something would fall, subject only to gravity on Earth, whatever that means. And in fact, it's defined evidently as essentially kind of an average of what that observed acceleration is at a latitude of 45 degrees. And once again, it includes centrifugal effects there. That's something you measure. And you can't measure anything but the combination of real gravity, if you want to call it that, and centrifugal effect. But for whatever reason, that's the value that they have defined as standard gravity. You always like to have a standard number, even if it's not applicable anywhere, right? That's probably applicable at some point, but probably only one point on Earth. Well, there's probably more than one point on Earth where that's true, but. So there it is, that value. And that value can be expressed as 9.80665 newtons per kilogram. And acceleration is a force per unit mass. And in the metric system, that's newtons per kilogram. And it's the same number. It can also be expressed, so I always kind of like 22 miles per hour per second. If you accelerate at 22 miles per hour per second, you are accelerating at an acceleration equal to g. And I just found out the other day, I guess the world record quarter mile now is some funny car that did the quarter mile in 3.8 seconds and got up to a speed of 340 miles per hour. So that's something like, a little less than 100 miles per hour per second. This car accelerates at something a little less than 100 miles per hour per second. Turns out it's a little more than 4 Gs. And that's a pretty amazing thing if you know anything about tires and frictional coefficients of friction. Getting a car to accelerate, a non-rocket car to accelerate at 4 Gs is really a testament to the tire industry. That turns out to be 35 kilometers per hour per second for anybody who cares to know. One of the things I like to note is that the acceleration due to gravity, standard gravity, whatever you want to call it, is also about one speed of light per year. If you accelerate at g for 1 year, you get up to a speed a little greater than the speed of light. Really? No, not really. But if you could do that, and somebody could see you doing that, then you would be traveling with respect to them at little more than the speed of light. That's just that's a happy accident that accelerating at 1 G for 1 year gets you to the speed of light. But that can also be expressed as 2.2 pound forces per kilogram. 2.2 pound force is the same as 9.80665 newtons. Notice that those last two are essentially can be viewed as mass to weight conversion factors. They're mass to weight conversion factors on the surface of the Earth. If you have a mass of 1 kilogram, it has a weight of, I would say, of 2.2 pound force. Ben would say it has a mass of 2.2 pounds, and he'd be right too.
No, I wouldn't. I would say that it's a mass of 1 kilogram.
You would, that's right. But if you had to say what it was in pounds, you would say it was 2.2 pounds. Okay, so that's G. And in Newtonian physics, what is G? It is sometimes a vector field calculable at every point in inertial space. It has to be inertial space by simply adding the contributions from every object in space. So what we do is we just take a point in space, we find all the masses in the universe, or at least the ones that are near enough to have much of an effect, and we multiply that mass by the universal gravitational constant, capital G, determined by Cavendish in the late 1600s. We multiply the mass by that, and we divide by the square of the distance to that mass. And then we take the vector g1, the contribution from that mass, to be toward that mass. And then we do the same thing for the second mass and the third mass and the fourth mass. And if we have to, we divide each one of those masses up into a million little pieces. And we take each one of those pieces and we do the same thing. If the thing is big enough and near enough, we might need to divide the Earth up into a bunch of pieces and find the gravitational effects of each piece, doing the same kind of thing. And we just add them all up. In calculus, we integrate over all of those masses. And we get a thing called the gravitational field. And I've shown a diagram there for the gravitational field. A vector field can be indicated by lines of the field. This would be the field due to two masses, one of which on the left is a little bigger than the one on the right. And you notice that if I'm very far away from these two masses, it doesn't show it far enough out, but if I'm very far away from these two masses, the gravitational field just kind of points toward both of them, toward the center, between them, maybe some point in the vicinity of them. But as you get closer and closer, the field tends more to point toward the big mass, unless you're really close to the small mass, in which case it might point toward it. So most of the field lines end up kind of running into the big mass, just because it's a bigger mass, and some of them run into the smaller mass. There's a lot more I could say about field line representations. But this is the complicated way in which we think of the gravitational field in Newtonian physics. And when we're done with this, we don't even get a thing which corresponds to the weight of an object on the surface of the Earth, because there's nothing in this that takes into account the centrifugal force. So after having done all of this, I then have to add the centrifugal force to get what I actually see as my weight. And that's the Newtonian paradigm. And it's a good paradigm to use because while it's complicated, it's calculable. And you can calculate it, and you can get, because the gravity in the vicinity of the solar system is so-called weak gravity. It's nothing like black hole gravity. The Newtonian approximation to general relativity works perfectly well for calculating orbits and all of these kinds of things. I can do this, and I get results, and it all works. But it's worth at least understanding that in general relativity, G is a much simpler thing. In general relativity, G, the so-called the so-called gravity, or acceleration due to gravity, if you want, the conversion from weight to mass to weight, whatever you want to call it, it is simply and always the observed acceleration of nearby free-floating object, period. That's it. If you see an object that is freely floating nearby, that is to say, not subject to any forces, then its acceleration is g. So on Earth, when I see an object falling, I measure its acceleration. That's the gravitational field. It agrees with the, doesn't agree, I shouldn't say it, it doesn't agree with Newtonian physics in the sense of giving you the gravitational field, but it does give you the thing that we always call the gravitational field. It gives you what down is. It gives you the acceleration that things have nearby. We say due to gravity, even though it's not. It has centrifugal force in it. And that's it. In general relativity, acceleration due to gravity is what you see it to be. And when people are in the space station, they see nearby free-floating objects having no acceleration. So G is 0. On the moon, you drop something, you see it accelerate with 1/6 the acceleration it has on Earth. That's the G field on the moon. In a car turning to the right or to the left, a freely floating object will kind of fall and move in the opposite direction you're turning. That's the acceleration due to gravity in that reference frame. That's G in that reference frame. G, you don't have to be in an inertial reference frame. You can be in any reference frame you want. But G is explicitly reference frame dependent because it's the acceleration that you observe a freely floating object to have. And the weight of an object is just the force required to prevent it from accelerating. On Earth, if an object will accelerate at 9.8 meters per second down, the weight of that object is simply the force that I have to apply to it to prevent it from doing that. If I want to hold something in my hands that it's not accelerating, then its weight is the force that I will have to apply to it to keep it from doing that. Now, none of this says that you can't use this to calculate anything. Right? It doesn't. There's no calculational paradigm. No calculation paradigm. There I go with that word. There's no calculation program attached to this. General relativity does have a calculational program. It's really complicated. You don't want to use it. But that doesn't mean that you can't layer it on top of the Newtonian paradigm to kind of have a simpler understanding of, why gravity looks different in different situations. And that's really kind of the point of what I'm trying to say here today. So I just have a summary slide and then I'll quit. But does anybody have any comments on that before I do that?
I do have a question, John. You used a word about 5-10 minutes ago that I had never heard before. Can you define, if I'm pronouncing it right, spaghettification?
Oh, yeah. So it's common when people talk about falling into a black hole, and it's something that happens as if you take the simplest case of a black hole, that's what's called a Schwarzschild black hole, just a mass that is not rotating, is not charged, that is just collapsed literally to a mathematical point. And then you ask about the gravitational field outside that. The gravitational field, first of all, the gravitational field gets stronger and stronger, but it also, for instance, let's suppose your feet were 1 foot away from this black hole and your head was 7 feet away from this black hole. Well, the force on your feet is enormously larger than the force on your head. Your feet are getting sucked in, if you want, to the black hole much more powerfully than your head is. And simultaneously, your sides are being attracted toward that point. And therefore, because they're being attracted to the same point, there's a squishing force on your side. Right? Every part of you is being attracted to a literal point that is only, a few feet away. And so what that tends to do is elongate you along the direction away from the black hole and squish you in the direction perpendicular to the direction to the black hole. And that whole process of what we call tidal forces ends up producing what we call spaghettification.
Could I ask one short follow-up question on that? I know there's an area around the black hole which is either called like the point of no escape or the point of no return.
The event horizon.
How far is that from the black hole, if you know? Thanks.
Yeah, so that depends on the mass of the black hole and is directly proportional to the mass of the black hole. It turns out to be, excuse me, I think it's 2, but it's the universal gravitational constant times the mass of the black hole divided by the speed of light squared. So for the Earth, that event horizon, I think, is like, a centimeter or something.
Golf ball sort of size, yeah, a little bit smaller.
Yeah, right. So, and that's the point at which, if you were falling into a black hole and pointing a flashlight outward, it's the point at which the light coming out from the flashlight, even though it would be moving away from you at the speed of light, would still be moving toward the black hole itself. So it's the point at which nothing, not even light, can get further away from the black hole. Outside the event horizon, when you shine a light, it will move away from the black hole. At the event horizon, it simply stays there. And inside the black hole, light moving outward actually moves toward the center of the black hole. Sometimes people think about this in terms of space itself being kind of sucked into the black hole so fast that light can't move. That's not exactly right, but it's not a bad way to think about it.
Thanks, John.
Mm-hmm. So let me just say the closing words here. There is a lot of confusion around the difference between mass and weight, as we've talked about here. And I think it has its roots in the fact that mass, as in quantity of matter, is almost always the thing that we really care about. How much stuff is there? Even when we're talking about weight, we're often really interested in the mass. How much gold do we have? How much stuff is? How much fat is there in our bodies, etc. Our simplest way of determining the mass of an object depend on it having weight. Spring scales and balance scales all depend on mass having weight, even though the weight itself is not really what we're interested in usually. And then finally, the fact that we live on Earth, where for all practical purposes, this conversion between mass and weight, G, is constant. So it doesn't matter. I mean, if something is twice as heavy, it's twice as massive. If the gravitational force on it is twice as great, it's twice as massive. So it doesn't matter whether we use weight or mass, and that's all kind of caught up in the definitions that we saw at the very beginning there. There's no downside to confusing weight with mass in most situations. But it is seriously compounded by the fact that weight, as it is generally understood, the thing that bathroom scales read, is explicitly not the force of Newtonian gravity. Yeah, even in the Newtonian paradigm, it's just not. It's compound. It's convoluted with the centrifugal force in that case, and in other cases, if we use bathroom scales, like on spaceships, we could use bathroom scales, but they would clearly not read Newtonian gravity. They read the force that you apply to them, and that's not the same thing as the gravitational force on you. And it's further compounded by the fact that astronauts are weightless, they clearly have mass, and they are very much subject to the Newtonian gravitational force of Earth. There's clearly a gravitational force acting on them if you believe in Newtonian gravity. They clearly are weightless, and they clearly have mass. All those things are just, how do you reconcile all of that? And I just, as always, I just recommend that while the Newtonian paradigm is infinitely preferable for working problems in the weak gravity of the solar system, we will always use the Newtonian paradigm because it's simple and it provides perfectly correct results to within our ability to distinguish. General relativity offers a massive conceptual simplification, and that simplification can be seamlessly grafted onto the Newtonian paradigm without actually using general relativity. It's just taking the conceptual framework of general relativity and grafting it onto the Newtonian paradigm can help you kind of navigate a lot of these confusions. And then I just have a link there to Bitophysics number 4, which I called fictitious gravity, and which I think Andy was the source of, I think, Andy's first real pushback against me, which I appreciate. I think he's right, and he's made me tone down my dogmatic gravity is not a force thing, which I still believe, but it's forced me to tone that down into acknowledging the fact that the Newtonian framework, where gravity is a force, is still preferable and will always be. There will never be a simpler way to work orbital mechanics problems when we're trying to send something to Mars or anything else. It will be what we always use because it's simple, and it's wrong. So those two things can be true at the same time. Okay, I'm done. So if anybody downstairs would like to come up, raise your hand. Anybody on stage? Oh, let's see, we have a new guy on stage. Who's that? Benevolent Entity. I don't think we've spoken. It's a name I don't remember. Did you have a comment or question, Benevolent?
Hello, how are you, Mr. John?
I should say, oh, Steve isn't here anymore. If Steve were here, I would have said, do you care? Because that's what Steve always says when that question is asked. But I won't. Go ahead. Did you have something you wanted to say? Or are you just hanging out with the cool kids?
Yes, I want to ask you a question. That what would happen if two supermassive black holes merge?
Yeah, well, I don't know if you ask that question. That sounds like I love that question because we have recently begun seeing that very thing happen. Are you aware of that fact, or is your question more innocent than that? That's okay.
No,
Yeah.
I'm just thinking that, as we know that our own galaxy is on a collision course with Andromeda galaxy over billions of years, and I wonder that what would happen if two supergiant black holes merge.
Yeah. Okay. Well, let me tell you, it's a really great question because in the last few years, Just a few years ago, we saw that happen for the first time, and we now see it happen, I think, on almost a daily, maybe a weekly basis. And I'll get to that in a moment, too. But first, I just wanted to mention that when galaxies collide, it's an interesting fact that very few things in the galaxies collide. A collision between two galaxies is usually manifest simply in a massive kind of tidal distortion of the two galaxies. They pass through each other with very few, if any, stars or black holes or anything else actually colliding in the sense that would make them merge or break apart or do anything like that. It's a gravitational interaction between two objects that are incredibly not dense, right? Stars are separated by enormous amounts of distance. And so when galaxies collide, very few things in them actually collide. And yet it causes havoc in terms of changing the relationships between things, causing them to move along different trajectories. Now, with respect to black holes merging, what we now know, I think, is something that we really didn't know a very few years ago, and that is that there are evidently lots of black hole pairs, binary black holes in the universe. And the evidence for this is that we see them in their final death throes, in the final milliseconds of their dance around each other, merging. And when two large black holes merge, they create enormous power. They put enormous power into gravitational radiation. I think the typical result is that effectively, well, so what you do is over the course of something like a second, maybe a few tenths of a second, something like 3 or 4 solar masses of mass is converted into energy in the form of gravitational radiation. And that gravitational radiation is observed by our gravitational wave observatories, the LIGO observatories on Earth. And that's become such a common thing, not only black hole mergers, but black hole neutron star mergers, that it's really kind of an everyday phenomenon now that people are talking about doing gravitational wave astronomy because of the fact that this thing happens so often. When first time it happened, 10 years ago maybe, something like that, it was big front page news. And maybe the second and third time there was some news about it too, but it's no longer news because it happens so often. And what happens is you form, well, first of all, two black holes orbiting each other are constantly emitting gravitational waves of fairly high power. And because they end up spiraling into each other. When two orbiting objects radiate energy, they spiral into a closer orbit, a closer lower energy orbit. And as that happens, they get closer and closer together. The radiation ramps up in power. And in the final second of that dance, when the event horizons begin to merge, the power is so great that the merger happened. The final amount of merger happens very quickly. And that's where you see this radiation of 2 or 3, 4 solar masses in the form of gravitational radiation that we then see something like 1 billion years later. Most of these things have been determined to be events that happened about 1 billion light years away, and yet we detect the gravitational radiation from them. So I'm sorry, that's kind of a long answer to your question. I'm not sure it was specifically what you were looking for. If you're looking for the actual kind of shapes of that, you can find things online where they actually kind of simulate the actual process, what general relativity has to say about what that process looks like. But I won't go into that here. Did that? Yeah, okay. I'll take that as an answer. Les, I realize I must have skipped over you. I see you on stage as well. Did you want to say something or have a comment or question? maybe Les is. Oh,
Well, I
there you
just
are.
want, no,
Hey,
I
Les.
just, you know, you were just a mind reader, maybe a wee bit psychic because you answered my question.
Oh, just now?
No, it was, what was, how can, you know,
Oh,
did you have to account for weight versus, weight versus mass on Earth?
oh, okay, good. Sorry, I didn't. Maybe you've been up here for a while. I'm sorry, I didn't see you until just now.
Well, I didn't have my, I didn't give any indication either.
Okay, good. Well, that's good to have you on stage. Hey, dude. Hey, dude.
What's up? I just
Don't
want to
bring
know
me.
what's your take on psychic phenomena?
Oh no, you have to get you and Hermes to have a room.
Nice. Well done. Well done. Well, it's peer reviewed, so it's science. It's been proven to be true. There's academic papers that say so.
Oh, there goes Benjamin
There's
again.
I was
universities,
kidding. I was kidding.
universities that support this research with tax dollars. It's science, man. It's science.
Benjamin's got his. What's that guy? Aaron Swartz. Is that the guy's name? Benjamin's got his Aaron Swartz hat on here.
I think Avi Loeb would be a closer fit for this
Okay.
CSB sit.
All right. Okay.
Can I,
Well,
can
let's.
I,
Yeah.
can
Go
I
ahead,
ask a
Shamash.
question?
You had a real
yeah,
question, did you? Yeah.
a real question? I mean, I can't
Comment.
have a fictional question, can I?
Well, I don't know. I thought we just heard a couple. Maybe not.
No, this one hopefully will be like a more real question. So, um, even in the Newtonian sense, right? I always struggle to think of all the variables involved when we do the calculation because okay, we are on the surface of the Earth. The Earth is the closest body to us. However, we know that the moon is around, and although the moon is smaller and weaker, etc., but we know that it exerts a huge force that moves the tide. It's responsible for all the tidal phenomena we see. And of course, because we rotate around the sun, the entire planet, so us and the moon, and we are also inside the gravitational field of the sun. When I'm stepping on the scale in the bathroom, right? It's very easy for me to imagine that the planet, is responsible for this. But I think the math is indifferent to the fact that other planets are also participating. I guess my question is, how much are these errors relevant to me weighing myself in the bathroom, like the other planets and the sun and the galaxy and whatever?
Yeah, that's a great question. Excuse me. It's a great question. The when the moon is overhead, we weigh a little bit less than when it isn't. That's the short answer to your question. When the sun is overhead, we weigh a little less than we do when it isn't. And when the moon is on the other side of the Earth, we weigh a little less than when it isn't. And when the sun is on the other side of the Earth, we weigh a little less than it isn't. And
during day and night as well, because we're further away from the sun.
You mean because at night we're further away from the sun?
Yeah, like because the planet has rotated, so we're facing backwards somehow.
Well, to the extent that's a very small, if that's even a smaller effect than the one that I'm referring to. But yes, that's true. That is an effect as well. The fact that we're a little further away. On average, we're at the distance of the center of the Earth, and then at midday, we're a little closer to the sun, and midnight. But that's not the thing that causes the effect. The fact is that we are being attracted, when the sun is directly overhead, we are being attracted to the sun a little stronger than the Earth is, because the Earth on average is being attracted to the sun by the distance that its center is from the sun. So maybe that is the same effect. The point is that the difference it makes during the day is a little bit bigger than the difference that makes at night, just because of the inverse R squared nature of the force. But that's a very small effect. But that is the effect that causes the tides. If that weren't the case, there wouldn't be tides. So it certainly is the case that we weigh less when the moon and the sun are overhead than when they aren't. We are literally pulled away from the surface of the Earth just as surely as the centrifugal force tries to throw us away from the surface of the Earth.
But isn't the surface of the Earth also coming with us? Like, I don't like this is a pet peeve of mine. I hate, oh god, the scene in the three body problem. I freaking hated this when everything started floating up in the air because the star came closer or something like that. I'm like, no, it
Oh,
wouldn't work that way. Like, it's not like some things are pulled by gravity, and other things aren't. Like everything would be moving with it. The planet too. I mean, there's not like the things aren't that rigid on a big scale.
well, there is a
Um,
thing called what is it called? Roche, the Roche limit. When a you can't form a moon from debris around a planet if it's trying to form too close, right? The gravitational force that holds the stuff together would be weaker than the differences in the gravitational force due to proximity to the planet, for instance. Yeah, it is the case. It is literally the case that if the Earth were orbiting the sun, or maybe not the sun, but if the Earth were orbiting a body that were compact enough for it to get this close, there would be a point at which an object on the surface of the Earth would be pulled off of the Earth to that object. Of course, the surface of the Earth itself would be pulled off the Earth to that object as well, to the extent that it wasn't, a ball of iron, unless you had something that was stuck to the Earth. The point is that you can have a lifting force that's greater than the gravitational force of the object itself. So that's actually a thing that can happen. It can't happen without, if there's oceans, for instance, the oceans will be lifted off the Earth too by the same effect if it's big enough. And to be big enough, I'm not sure the Earth could get close enough to the sun for that to happen. But if you made a sun mass thing smaller than the sun, then there would be a point at which you could have an Earth close enough where that would happen. Does that make sense?
what was that word? What was that called? The something limit?
Roche limit,
Roche limit.
Roche. Look up Roche limit. Yeah.
Okay, I've never heard that before. Cool, thanks. But at that point, like the moon or the Earth or whatever it would be sheared apart, right?
Yeah, that's right. That's right. At the point that you do that, unless the object itself has some rigidity, glue-like rigidity, it's going to be torn apart itself. That's right.
I got a lot of stuff in my house that's not fixed down, so it would be a mess.
Yeah, Les?
Please ignore this question if it is sort of off topic or too complicated. There's the Higgs field and Higgs boson, and is there a simple way or a way to that would be understandable to meet the connection between that and weight?
And mass, yeah. If there is, well, I think the answer to your question is no. The answer to another question, do I know of one, is also no. I don't think there is an explanation that would be understandable even to me, frankly. But I know for sure that if there is one, I don't know what it is. That's something. I mean, let's put it this way. I mean, I understand the sense in which. We talk in quantum field theory, we talk about, everything being a quantum field. And so there is a quantum field for mass, and the Higgs boson is a particle. All quantum fields are associated with particles. I get all that language. I don't really know in any fundamental way what that means. And I certainly can't convey to anybody else what it means because I don't know myself, even though I know the words. So that's not my field. It's over my pay grade.
Have you heard the cocktail party metaphor?
No, go ahead.
I'll probably I'll bring this up only so people can go look for it. And I think I heard this from, I don't know, some
Brian
some
Greene and Neil deGrasse.
Yeah, where like the idea is like I could walk around a crowd at a cocktail party and not be impeded too much. But like if a famous person were to come in, everybody would come like talk to them and they would be like impeded and that was this is supposed to be a metaphor for how like some things are affected because of their mass, and it kind of slows them down. Actually, I think I'm bungling it up, but I think Brian Greene tells this better if somebody wants to go look for that.
Well, I think I've heard that kind of a thing talked about before. I think the thing that I always get bogged down with is all the metaphor, analogy type things that I've ever heard seem to at some level confuse velocity and acceleration. Like I get there being an impediment to moving. I don't quite understand an impediment to acceleration. I don't know if you know what I mean. It's somehow the analogy breaks down for me because I don't understand what it really has to do with inertia. It sounds more like viscosity or something than inertia, a force that's dependent on velocity and not one that's dependent on acceleration. I don't know.
Plus, it doesn't explain why certain particles are more massive than others. It just tells you, oh, they are interacting more with the Higgs field. Yeah, why? So the analogy completely is oblivion. Like I can live with the blue fairies, right? Let's include the blue fairies in the theory. But what's the extra story here? What's the details? The analogy just leaves that under the blanket.
Yeah. No, I think the thing that I find most compelling about the Higgs story is, just as with most things, that it took quantum field theory, which is an incredibly successful theory in physics, and kind of said, well, one entailment of that theory is there should be this particle, a particle of the Higgs field that imparts mass. I don't know what that means myself, but people who are experts in the field did enough to predict and then to kind of work out likely energy ranges, and then there it was. When you discover something that is a bizarre prediction of a bizarre theory, it's just, I find that more compelling than finding a bizarre thing and then coming up with an explanation for it.
Plus, Higgs was alive when they found it.
Yeah.
That's the touching. I that video is played every year at the end of the year in my class. The video of Peter Higgs sitting there crying.
Yeah, it is a great video. Hey, Richard, welcome to the stage. Do you have a comment or question?
Sure. Yes, I did have a bit of a question. Gravity. All right. The acceleration due to the curvature of space-time, as it's explained in that form. The degree, is there a relationship between the degree of curvature and the acceleration that's created?
No, because there is no acceleration that's created. Any acceleration that you see is simply the result of you accelerating relative to freely falling objects. When you see a freely falling object accelerating, it's because you are not in an inertial reference frame in relativity. In relativity, inertial reference frames are always local, meaning confined to however small a volume you need to make it so that you can't tell that there's a difference.
Right.
And on surface of Earth, inertial reference frames all fall in the direction that things fall. If you release something from your hand, that thing is now in an inertial object. And so you see it accelerating downward. That's because you are accelerating upward relative to local inertial frames. So whenever you see a freely floating object accelerating, it's because you are not in an inertial reference frame.
Okay. And if, for example, let's say using black holes, if you have a black hole, an interesting observation, just an aside, the idea of finding pairs of black holes, wouldn't that be somewhat connected to the finding of binary stars, in that black holes or stars are failed black holes? They just never had enough mass to collapse.
I don't,
Let me expected maybe.
So let me just say about that, and then I'll let you continue. I don't know what the thinking. I think that this new discovery that there are lots of really massive black holes in the intermediate mass. These are 20, 30, 40 times the mass of the sun. That there are not only a lot of them, but that there are a lot of them in pairs, binary pairs that are nearing their end of their life rapidly enough that we see one every few weeks or something. I don't know what the frequency is of that. Is a very odd thing, and I don't think it can be maybe it can be understood in terms of early stars, because early stars were very massive stars, early stars in the stage of the universe. It might be just explainable in terms of how many of them there were, how many of them went supernova, became black holes, and they were binaries maybe already. So I don't know where they come from, but it's a very odd thing, I think. I think everybody thought it was very odd to discover that. Anyway, that may or may not have anything to do with what you're saying. Go ahead.
Oh, sure. Well, no, just suggesting that the prior discovery was that there were a lot of binary star systems. That would suggest,
Right.
an ounce of mass, in proximity to each other that would create that. And that because, black holes often are, produced by obviously mass or stars going supernova and collapsing, that if you would find binary stars, then you ought to expect that there would be pairs of black holes in that regard. That I thought should have been expected as opposed to being a surprise.
So I think what I was starting to say then was pretty much right on point. Yes, most stars are in binary systems. That's the mode. That's not a rare thing. So there is that to begin with, but it's also the case that most stars we know about are not big enough to leave 30 solar mass black holes in their wake. So that's the part that I think was a surprise. I don't know for sure, but I think that was quite a surprise to learn that there could be so many massive binary pairs. Yeah.
True. Okay, so it's the massive part that's the surprise, not necessarily the binary part. Gotcha. Okay, because I was just curious about. Yeah. So the original line of questioning. All right. So thought experiment. If we were to just keep piling black holes, or combining them, one by one by one, adding black holes to black holes to black holes, does that only extend the event horizons? Is it just that you get a broader event horizon?
That's right.
Leading from that. But what about the effect of objects that are now trapped by it? So once they're in it, they, I hope I'm using it right, fall to the center, or they're pulled to the center of the curvature of space-time in that localized area at the same rate, no matter how many black holes or how much mass is in the center of that. It doesn't, the increase in mass doesn't change the rate by which things accelerate or falls towards it.
Well, so there's a lot of things going on there to kind of take into account simultaneously, to the extent that the two merging black holes, had accretion disks around them, which is probably not likely. If you have a binary black hole, I'm kind of assuming that any accretion disk, you usually have an accretion disk associated with a single black hole. If you have a pair of them, that's a good question. I don't know about that. At any rate, the gravitational field, it just goes, if you had a black hole twice the size, then you can say in some sense, certainly outside the black hole, the gravitational effect is simply doubled if you have twice as big a black hole. Within the black hole, the event horizon gets further away simply because of the fact that the gravitational effect is doubled. It's kind of that simple. Now, what the details of what goes on inside a black hole are, subject to a lot of speculation for kind of obvious reasons. We're never going to see it, or if we will, we'll never be able to report back. I did my undergraduate thesis on that at a time when it was thought that there were these things called quasars, which had recently been discovered. And it was speculated for a while that quasars might be white holes. They might be the other side of black holes, because if you look at the solution to Einstein's field equations for a rotating black hole, which all black holes are. All black holes have some rotation. They include this throat-like structure through a ring singularity. And it was thought at the time that, in fact, we knew for sure that most things, most trajectories didn't actually go to the ring singularity. They just ended up on kind of orbits around the inside of the black hole. And some of those orbits actually take them out of the black hole into a region of space-time that looks completely normal. And so the idea was maybe black holes were the kind of the input side of white holes, even though it wasn't understood why it wouldn't happen in both directions. If you had a black hole, it would also be a white hole. You'd have stuff coming out that had fallen in the other side. And this was where kind of the idea of wormholes first originated, that these things might be passageways to other parts of our own universe that were spatially separated, et cetera. And that's moved a long ways. I didn't do my career wasn't in that. I don't know the details of what people don't think that you can have a stable wormhole of that form anymore. But anyway, connected with that is just the question of what does happen ultimately to stuff that falls into black holes, and that's the subject of all sorts of still research, speculation.
I'm just wondering that if they haven't yet determined an upper limit for the ultimate size that a black hole can be, could that maybe explain what they call the great attractor?
I don't know about that, but you've probably heard there's been speculation for a long time that the universe itself might actually be a black hole. If you take the total mass of the universe and its size, you get if you take the total mass of the universe and you ask what the event horizon radius is, you get a radius that's not very different from the size of the universe. And so, so that's, and I don't know what that means. Sorry?
The 90 billion light years or the 15 one, the observable?
I don't know the answer to that question too, but let me just say it's the point is it's not thousands or millions of light years, it's billions of light years, right? So you're getting an event horizon that at least is on the order of the size of the universe itself. And I don't know what you make of that. If the universe is a black hole, what does that even mean? I don't know what that means. But it's at least kind of, it's suggestive that if you think about the cosmological solution to the field equations and the black hole thing, it all kind of sounds compelling to think that it's just, that's the same thing. I don't know beyond that. I don't know how to interpret what it would mean.
Thanks, John.
Yeah. We very quickly get above my pay grade and you start to appreciate why I do these bites of physics. Go ahead, Benjamin.
Isn't the Roche limit related here? The Roche limit is what? The collection, the density, it's
basically the radius at which a loose collection of particles cannot itself be gravitationally bound.
Cannot be gravitationally bound. Doesn't that mean you have a black hole?
Oh, no. Oh, I see what you're saying. No, not that at all. Roche limit is just a Newtonian gravitation idea. If I just took a bunch of particles and assembled them at some distance from a planet, there's a minimum distance that assembly would have to be such that it wouldn't be tidally disrupted. Wouldn't be able to self-gravitate.
I think there's another size, which if you take any mass, like the size of the Earth.
You're thinking of like a Planck radius or something.
A particular size, it becomes a black hole. And like for any mass, there is a corresponding size.
Oh, well, that's just the event horizon size. 2G, when 2Gm over R 2Gm over R equals the speed of light squared. You solve for R, you get R. I think it's 2. I think there's a 2 in there. 2Gm over C squared. It's the event horizon.
Like Roche. Well,
if
yes,
you
it's the
compress
event
something into its
horizon.
own event horizon, it's a black hole.
Yeah, but yes, but there is a definition. I thought anyway, there was a definition for just a diameter for any object,
Well,
which
that
represents
is a
its
definition for a diameter. It is the case. I mean, if you want to make an electron into a black hole,
formula for it. I thought the formula had a cute name. That's all I'm saying.
yeah, I don't know what it would be other than the event horizon. Event horizon, it's the radius of the event horizon, basically.
I think for the Earth, it's like the size of a basketball. I think it would fit on a T-shirt.
Yeah, we were talking about that a
Also,
little
I could be
earlier. I think
wrong.
it's a centimeter or two for the Earth. So you might be thinking of what is the sun is more. What is the sun, a kilometer or something? Can't remember. No, it can't be that much. Anyway, yeah, we could work it out. Let's see. Let me try to work it out here while we talk. If I take 2 times
I just thought it had a
6.67
name.
times
Nobody remembers the name?
divided by. Oh, wait a minute. Oh, well, I don't know.
Wait,
I
we
thought I
have it in
gave it a
the.
name.
It's called the Schwarzschild. Called
Schwarzschild
the
radius. Yeah, that's
Schwarzschild
the
radius.
radius. Okay, that's a good name. But that's the radius of the event horizon. Yeah.
Yeah, sort of. I don't even know that that's true.
But it's true. Trust me. The Schwarzschild radius is the radius of the event horizon for a black hole.
Okay.
When we talk about a black hole, a lot of people think a black hole has a size, right? But you go through the event horizon, it's just space. It's just a distance from the point at which all of the mass is assembled. In the case of a Schwarzschild, Schwarzschild radius is really only technically applicable to a non-rotating black hole, and there aren't any non-rotating black holes. Just kind of by an argument that would have to do with sets of measure 0. There's no object doesn't rotate, and so there's no black hole that doesn't rotate. But there, you can imagine a black hole that doesn't, and that makes a very simple solution of the field equations, which is called a Schwarzschild black hole.
Black holes that rotate have pancake shapes. Event
Have what?
horizons?
Yeah, they do
Okay.
too, but the event horizon, they actually have, they rotate, they actually have kind of 2 horizons. One is, I can't remember the name, so one is called the stationary limit or something, and there's an event horizon, and then there's a stationary place where light can't stand still, which is outside the event horizon. If it's rotating, there's a place where light can no longer stand still, even though it can still escape, because space-time itself is being dragged around the black hole so quickly that there's no place closer than what it was. Oh, let's see. Am I saying that right? No, I'm not getting that right. I'd have to look at it again, but it has
So
to do
here's a
with light
fun
standing
way to
still.
connect the end of this talk to the beginning. And that is, since we've arrived at black holes, which is a natural place to end up if we start with mass and weight, right? Because in a way, the most extreme phenomena of mass and weight. But here's a question for you. Do black holes calculate well in a Newtonian framework, or do they require a relativistic framework to be
Yeah,
properly
no, you
calculated?
can certainly within Newton would have. I don't know if Newton did do this or not. No, he wouldn't have done this because he didn't have a good idea. But if you assume, as Newton did, that light is corpuscles, and you assume that for whatever reason those corpuscles travel at some speed, which is kind of a weird thing too. But if you assume that they travel at the speed that we now know is the speed of light, you can just simply calculate the given the mass of an object, what would its radius have to be such that escape velocity from its surface would be greater than the speed of light. And that would be a planet such that if you shone a flashlight shooting these corpuscles out at that speed, that light would necessarily not be able to escape the planet, and that would effectively be a black hole in Newtonian physics. escape velocity for the Earth, right, is 25,000 miles per hour or something like that. So you'd have to either have a lot more mass in the radius of the Earth or make the Earth have a lot less radius. And either way, you'd find it. And the formula you get is the same formula to at least within a factor of 2. There might be an extra factor of 2, but you get the same formula that you get for the Schwarzschild radius. You kind of have to, because the formula has to depend on the universal gravitation constant, it has to depend on the mass of the object, and it has to depend on the radius of the object. It has to depend on the speed of light, I should say. And there's only one way to put those things together to get a length. So that length you get is going to be that radius. I shouldn't say so it is, but if you make the argument that there should be such a radius and that it should depend on those things, the fact that there's only one way that you can put those things together to get a length means that has to be it, down to just a numerical factor. And to be really specific about that, if you have the universal gravitation constant and a mass and the speed of light, the only way to get a length is to multiply g and m and divide by the speed of light squared. And if you do that, you get the formula for the Schwarzschild radius, down to a factor of 2.
That I was slightly distracted by the potential for an IFR flight today. So you concluded that you could understand a black hole in Newtonian terms?
Yeah, you just simply let the escape velocity be the speed of light, and that gives you the relationship. Escape velocity from a planet is 2gm is the square root of 2gm over r squared. And so if you set that equal to the speed of light, you get r, and I believe the radius you get is the Schwarzschild radius. It's either that or it's that within a factor of 2.
What the orbit? The Schwarzschild orbit is the escape velocity? Why are you saying these are the same thing?
Well, so escape velocity is the velocity. So from Earth, escape velocity is 25,000 miles per hour. What does that mean? Does that mean you have to go 25,000 miles per hour to escape Earth? No. You can leave Earth at 1 mile per hour, and if you keep going 1 mile per hour, you'll leave Earth. But you have to have a powered rocket to do that. Escape velocity is the speed at which you just throw something and it escapes. Assuming there's no atmosphere, don't worry about atmospheric drag, right?
And so that relates to the Schwarzkopf's radius?
Yeah, so if you set that equal to the speed of light, you get the Schwarzschild radius. In other words, if the speed of, so the Schwarzschild, the escape velocity is 2gm over r squared. Set that equal to the speed of light and solve for r.
I think I can say this
over r, over r, not r squared.
I can say this back in a way that we talked about, and this is kind of fun for flat Earth, because the Schwarzkopf radius is the radius at which, for all intents and purposes,
not Schwarzkopf. That's something else.
What?
You said Schwarzkopf. He was a general.
Schwarzschild.
Yeah.
Schwarzschild. The Schwarzschild radius. If you were at the Schwarzschild radius, the Earth would be, for all intents and purposes, flat.
Would be flat?
Because light would travel. Light traveling in a straight line would orbit the planet. And it would be indistinguishable from flat.
Oh, I see. Well, I think that's not quite right, but I mean, you could make some kind of an argument like that. Basically, that's a refraction argument, right? It looks flat because, if light hugs the Earth, then you see, right? Light can come to you from every point of the Earth, and it looks like it's all out there in the same direction.
No, it's not. It's not refraction.
No, it's not refraction, but it's the same idea. Refraction makes the Earth look flatter than it is because of the fact that refraction makes light curve downward.
Look flat. It would be flat.
Well,
in a relativistic sense. The shortest distance between two lines, etc., would all be consistent with flatness.
I'm
at the
not
source
sure how you
child
make the
radius.
case of flat when you can make that for every point on the surface
But
of the
but here's
sphere.
the
But
thing: if you were going at the speed of light of the Schwarzschild radius, as you said, right, you would be exactly at the does not escape velocity. And if you went just a little faster, you would escape, and if you went a little slower, you would fall into the Earth
in a
or into the
Newtonian,
object.
you're talking about a Newtonian world.
Yeah, well, that's what you just meant to say, wasn't it? That the
Yeah,
escape
well,
velocity or
well,
black hole.
but escape. I mean, the only thing is that escape velocity isn't tangential velocity, right? That's a radial velocity.
Ooh,
I mean, it doesn't
tangential
have to
is
be.
not.
If
Wait,
you
isn't it tangential? I thought it always was
well, it can
tangential.
be if you shoot something from the surface of the Earth in any direction from an if you have a spherical, non-rotating, atmosphere-free Earth, and you shoot
Yeah,
something in any direction at 25,000 miles per hour, it will escape. That's true.
cool. I
But
like this notion that the Earth would be flat if it were a Schwarzschild radius.
yeah, but I think actually for flat you need the 17,000 mile per hour orbital. You need the orbital velocity to be the speed of light, not the escape velocity.
Hmm.
And that's a little
Yeah,
less.
but the theory is that the speed of light, if you were at the Schwarzschild radius, then light would travel because light travels at the speed of light. Light would travel in straight lines, and it would a flashlight pointed in one direction would hit you in the back of the head after it went around the planet. But it would be
Well, I think you're
traveling level.
so. Let's see. I mean, of course, we are speculating here on what it would look like in a corpuscular Newtonian theory of light with Newtonian gravity.
No. That was a different question. For
Oh,
this
okay. You're
particular
talking about in
illustration,
reality. Huh?
that Schwarzschild equals flat Earth. That's that's um that's a relativistic proposition. I don't think it makes sense in a Newtonian
So at the Schwarzschild
conversation.
radius, if you shine a light directly outward, radially outward, that light will just sit there. If you shine it tangentially, it'll hit the black hole. It'll spiral inward.
Um, well, it's a fine line, but if you're a little bit higher, a little bit lower, you
Yeah,
get different behaviors.
that's right.
So if
There
you're a
is
little
a
bit
there is
below
a
the Schwarzschild line, it should spiral in. If you're a little outside the
not, but it's
Schwarzschild
not.
line,
So the only mistake you're making is that's not the Schwarzschild. That turns out to be 3 times the Schwarzschild radius. It's called the light sphere, the place where light itself will orbit the black hole. I think it's 3. I might
oh,
be wrong, but I think it's at 3 times the Schwarzschild radius. You get,
way
and
too
when you see
cool.
these pictures of these, you've seen the pictures of black holes.
Yeah.
As I understand it, that what you're actually seeing there is essentially that 3 times the Schwarzschild radius. It's the sphere at which light is orbiting the black hole, essentially well, light is orbiting the black hole. It's
Can
not.
you explain this in a little more detail? Because that's really fascinating. So you're saying that the blackness is the Schwarzschild times 3, and the light coming around the blackness is because light orbits a black hole at the Schwarzschild times 3. But then
I
what
well, I was.
about the thing that
Go
looks
ahead.
a little bit like Saturn's moons? Sorry,
You mean this thing
Saturn's
with kind of
ring.
the bent ring thing? Is that what you're thinking of?
Yeah, the bent ring
I
thing.
think that's kind of that's
What
an
is that?
artist's conceptualization of what a black hole looks like if you take into account the gravitational lensing of the black hole itself. I
Hmm.
think I don't completely understand that picture, but it's definitely an artist's rendition. We don't have pictures that show that.
I thought we did have a bit of a picture. It
We
wasn't
do have
great.
pictures of just a ring. It just looks like a ring.
Like a Saturn's ring.
Yeah, that's
A
right.
bit.
Maybe
A
that's
bit.
what you're talking about, right? And as I
Yeah.
understand it, it has to do with the fact that there's heating there's an accretion disk that's heated or something. It's creating a
Does it
lot of
not have
light.
to do with the rotation direction of the black hole?
Well, I don't know what you mean by rotation direction exactly. It has to do with the fact that it is rotating. So it's accretion disks will always be, perpendicular to the spin axis, just kind of by
That's what I
virtue
meant.
of what happens to orbits of things like that if they're not.
Accretion disk. What is that? Is that junk that is
Stuff that's on its
close but
way
not
in. Yes.
fully?
Usually it's
Yeah,
in
stuff
the
saying
case of
goodbye.
black hole, often if you have a black hole orbiting a regular star, the black hole may be sucking material off of the surface of that black star, of that orbiting star, a Roche limit kind of a thing.
So
And
here's
that
a
stuff.
weird question. If somebody else has a question, they need to butt in because
Yeah.
they haven't. There's several times people.
Yeah, welcome anybody. If you raise your hand, I'm watching. So if you unmute or something,
just talk right over the top of me if you got a question. If a black hole, this is a funny thought. If a black hole is spinning, then won't space-time inside the black hole be sort of non-orthogonal, meaning that from an external point of view, distances along the spin axis will be longer than distances orthogonal to the spin axis?
Well, it's a complicated question. What things look like is something a little more difficult. You have a metric that basically tells you how to calculate the distance between neighboring points in space-time. And the effect of a rotation is ultimately that however you do that, space-time gets dragged. We see this around the Earth. There's been an experiment to actually detect the dragging of space-time around the Earth due to its rotation. And I think I don't know what the results of that are, but I think we've verified the relativistic frame dragging effect
Interesting.
in that sense.
I can't picture what dragging means exactly.
Well, it really means
I could picture if you took a melon and you squished it, that it would bolt on the other end. But how is dragging? If you had a
so it really comes down to the fact that
how would it change?
So in extreme cases, it manifests itself in an observable difference between the amount of time it takes to orbit in one direction than in the other. Right? So an orbit in one direction can be...
Are you orbiting in both directions? How do you do orbit? What? It takes longer to orbit in the direction of spin than it takes to orbit in the direction that's against the spin?
Well, it would be the other way around, presumably. But yeah, frame dragging would mean essentially that the frame dragging helps you in one direction and hinders you in the other.
You're saying that we have evidence of frame dragging in the Earth, so we've been able to.
Yeah, let me look up this. I can't remember, gravity probe B or something satellite. Let me see.
That's pretty cool. Dr. Laird should know this stuff. That's kind of almost astronomical, isn't it?
Say again.
I wonder, doesn't this qualify as astronomy?
Well, I wouldn't call it astronomy. I mean, it's not something. Gravity probe B is the satellite. If you want to look up gravity probe B.
Is it cosmology? What? Is it not?
Well, it's just testing a prediction of
like black holes.
It's just testing a prediction of general relativity. One prediction of general relativity. The metric. So what you do in general relativity is you have the field equations. You input and you look for a solution that maps onto a rotating mass. So you have a mass and you have an angular momentum. That's basically it. And if you have a mass and an angular momentum, general relativity predicts that rotating mass will have this frame dragging effect. And you can read about it if you look up in Wikipedia, gravity probe B. What do they say about it? So they've confirmed the predicted geodetic effect, as it's called, to an accuracy of about 1%. One of the things this does is it causes anomalous precession of gyroscopes. And so I think Gravity Probe B has a gyroscope. It has a rotating sphere that is captured inside the satellite. As I recall, I may be getting part of this wrong. The satellite has thrusters on it that make sure that this rotating sphere never touches anything. So it's monitoring the rotation and therefore the precession of the spin axis of this sphere without ever letting the sphere touch anything.
Magnetic repulsion?
No, it's just following an inertial trajectory. In other words, what you make sure is that there is no force on this rotating sphere, and you monitor it by having it fully inside a satellite that adjusts its trajectory so that it never touches that sphere.
Oh, the satellite moves.
Yeah, if it needs to.
Maybe. Okay, but here's the final landing question. If we can measure frame drag, if we were in a black hole, by your own axiom, that black hole would be spinning. If the Earth were in a black hole, if the whole universe, in other words, were inside its own event horizon, then by your claim, all black holes spin, then the black hole that we are must be spinning. Therefore, it must have frame dragging, and we should be able to detect that frame dragging separating it from our own frame dragging might be like impossibly hard. We might have to get off the planet to do it, et cetera, et cetera. I don't know. We might have to get out of the solar system to do it. Could we send the next Voyagers with this instrument that could detect the frame dragging of the entire universe? And if we could, would that be evidence that the universe is rotating at least?
Yeah, well, I'll just say that I don't know how to answer your question. There's a lot of stuff. There's a lot of things I would need to understand better before. In the case of the Earth, for instance, we know what the mass and angular momentum are, so we can put them into the Kerr solution, as it's called, of the general relativistic field equations. We can calculate how much frame dragging there is, and then we can see with this geodetic effect, the precession, anomalous precession of the gyro, whether that agrees with that. In the case of looking for some frame dragging effect for the universe being a rotating black hole, I don't really know what I'm putting into that. I don't know what I'm looking for. And there's a lot of other things I don't understand well enough to even really generate a question that I would be trying to answer. I guess that would be what I'd say there.
Fair enough.
So anyway,
Nobody else have
good.
Any questions? Nobody? Questions? Andy?
Doesn't look like it. Did you have another?
No, I just wanted to dissuade you from your religious belief in speech action at a distance.
Okay. Well, I think that's probably a good. But anyway, that was a reasonable discussion. I mean, I think there's hints there of things. That wasn't completely off the wall, but I think it takes us into areas where it is really important to understand that you need to kind of know what it is you're talking about before you send satellites up and look for it. In the case of the geodetic effect that they're talking about here with the Gravity Probe B, we knew exactly what it is we expected to see, and so you can then check and see what that is. It's nice to have that idea before you go looking for something. Anyway, okay, I think maybe I'm going to shut this thing down. It's been fun, and we'll see. I will confess to feeling a little bit like I've been letting these things go to the last minute. This morning was really it. I thought I wasn't going to do anything today, and that may happen in the future. But we'll see. I do want to get back to my Newtonian mechanics thing. Maybe we'll pick that up again next week. thanks for coming, everybody. And let's see. Maybe I should let Shamash. Shamash, you want to say again one more thing about what you're going to do next Wednesday on Philosophy Wednesdays?
Yeah, gladly. Thanks. Thank you, John, for the presentation. By the way, that was a pretty cool. I've personally, gravity is one of my favorite topics. This is where things
Mine
get.
too.
Yeah. This is where things get interesting. So yeah. Philosophy Wednesdays, I've started, the idea was to introduce philosophy to a scientific audience. Today was somewhat of a nice philosophical room, by the way, John. This went in some corners. You could use these as standard examples. The discussion with the what how do we define a force? How do we define weight? How is it that things change, etc. We were talking about a certain man called Thomas Kuhn. Thomas Kuhn was a physicist, and he is thinking about, he consecrated his life to study how science evolves. So the way we discover a new idea, like, for example, today, gravity had a different understanding with Isaac Newton. And then after the Einsteinian work, we now have a completely different understanding. And you heard people joke around about gravity being a fictitious force, so to say, where it wasn't back then. It was the force to study. So we will be talking about more around what is it to have a scientific revolution, how scientific change happens, and how is it that people sometimes push the change, sometimes resist the change. Last time that was the topic. Tomorrow we will, next Wednesday, 17:30 GMT, same time as this room, we will be talking more about the shortcomings of his views about a paradigm, if you've heard the word before, and how this paradigm shift happens. And what are the constraints and the limitations of looking at science in this way, that because it kind of makes it like a religion in some way. So yeah, this will be the topic for next Wednesday, and if you're interested, please show up. Thanks.
All right, thanks, Shamash. I think I'm going to play us out with a tune for no good reason. This is a tune. This is for Andy a little bit. I recorded this tune in a recording studio right across the street from the Bay Model.
Before we play music, Elliot writes in the chat, maybe next time we could talk about how quantum mechanics suggests there can't be infinite densities, so no singularity.
Yeah, that's a good point. I don't know that I think there's a whole bite of physics necessarily to devote to that, but I will just say I think it's a good point. It has to do with, it's right at the heart, really, of the thing that people talk about when they talk about the kind of incompatibility between quantum mechanics and general relativity. General relativity being a classical theory, non-quantum mechanical theory, doesn't deal nicely with what happens. According to general relativity, a black hole, a Schwarzschild black hole in particular, would be all of the mass would be confined to literally a mathematical point of zero volume. So you would have infinite density. And there's every reason to think that quantum mechanics would have something to say about that. And even a rotating, excuse me, even a rotating black hole where the singularity takes the form of a ring would still be a ring of zero volume, and so you'd also have an infinite density. So even in the more practical case of black holes that we have, you would have that happening.
Wisdom is asking, are you telling me there are no realized infinities? I think he's being a little bit cheeky.
I'm hoping he's being cheeky there. I don't know. He could come on stage and tell me.
There is a kind of inverse infinity that we do seem to realize, and that is superconductivity. So two questions there. Do you think that superconductivity represents a kind of inverse infinity? And do we realize it?
That's a good question, and I don't know. That's an interesting question because I don't know if in reality we've ever created a current which to all measurement In other words, you should be able to establish a current in a superconducting ring that stays at whatever value it is forever. And I don't think we've ever, I know for sure we've never done that because, of course, we'd have to wait forever. But I don't know if we've ever established a current like that and then watched it and not detected it to decrease for reasons that may or may not have to do with the non-superness of the conductivity. In any event, you might expect the current to reduce simply by energy draining off by any of many mechanisms. This is really outside my field of expertise, but I know what you're saying. If we genuinely have superconductivity, zero resistance, literally zero resistance. That's a kind of an inverse infinity, I think, and that's what you're referring to. It's a good question, and I don't know the answer to that. I think quantum mechanics does, in some sense, predict. I think quantum mechanics predicts that the conductivity is literally zero. I may be wrong about that, but I think that's the prediction you get, and there's probably good reason to wonder if that's physically reasonable. That's about all I'd have to say about that. Okay, yeah. So those are two good comments. As I said, though, I think I'm going to play us out here. This is a tune that I recorded with my friend Mike Johnson, like a lot of tunes I've played here in the past. This one happens to have been the only one that I ever actually recorded at the record plant in Sausalito, across the street from the Bay Model, the place that Andy rides his bike by every once in a while. So you can just think about the magic that happened inside those walls one time. 45 years ago, I think I recorded this. Yikes. Okay. See y'all later. Oop. Oh, wait a minute. Now we'll see y'all later.